Now we'll go to current slide. Okay, good. Sorry about that. I think I told you last time, looks like the trip to the planetarium is almost impossible at this point. There may be, I don't know if we want to try one more option or not, but it seems pretty distant possibility, so probably it's off. But I did want to, let's see, maybe run something by you today to see what you feel about it. If we were to end just a little early today, would y'all be too upset with that? Would you feel like I was cheating you from your tuition dollars?
Absolutely not.
Wow, y'all are such a forgiving class. That's just incredible. All right, I'm so lucky to have you. Okay. Something like that. What's that?
We're so lucky to have you.
Okay, wipe it off. Okay. No. All right. Where we left off last, first, any questions? All right. Where we are is in chapter 17, and the one reason I'm considering it, maybe slowing things down a bit. The trip to the planetarium was a full lab plus some extra time, so we've got that time we're not going to have to spend, so therefore I don't feel so bad about, moving a little more slowly maybe, but not too much. We're in chapter 17, and we'll do this today. I don't think we're going to finish 17 today, especially in 2 hours. Oh, wait, I'll take that back. We will finish that 17 today, I think, but it will not be, I don't think we'll finish in the first 2 hours, because we've already lost 15 minutes of it or so. So the odds are we are not going to have the lab for 17 today. I have it ready, or at least it's in the copy room, hopefully. I took it down there. Hopefully it got copied. And but I don't think we'll have time to do the lab. But we do have scheduled the test for chapter 16, which will be the last 30 minutes today. And I do want to make sure everybody has plenty of time to do it. It's not going to be any longer than any other test, but I just want to make sure you have time. So that's one reason I'm considering knocking off maybe a little early so everybody will have a good chance to finish the test. And then if you do finish early, you can go. All right. I don't think the lab will be an issue because we just aren't there yet. All right. That said, where we left off last time, any questions, anything, chapter 16, where we're going to have our test today, or about, was everybody here last time to get a copy of the lab for 16? Okay, you were not, okay. I knew there was something else I needed to ask you. Now, what you have to do, gracious, deep in here. What you have to do is listen to the YouTube video, okay? And maybe get with a partner, somebody who was here to fill in any details. If not, see me. You've got probably at least 2 weeks to finish the lab, because part of the lab you have to make observations, and that's going to be over an extended period. So you've got plenty of time to work on it, so get with somebody or get with me, and I'll try to help fill in any blanks. Listen to the YouTube videos. I think you'll be able to do most of the lab based on that, and all the instructions for the rest of it are there, but ask questions if you need to. All right? Now, that was one thing I meant to do. I'm blowing my mind. What was that other thing? All right, where we left off last time, we were talking about minerals. Remember, minerals are naturally occurring, not synthetic. Inorganic, meaning not coming directly from living organisms. and they have to be made up of rigid crystal structures. They're solids, by the way, too. Minerals are solids. Now, what we're launching into now is the physical properties of minerals. These are ways we classify minerals, and your lab for this chapter is basically this part right here, okay? And everything we do today, well, not everything, but a lot of what we do in this section here will directly impact your lab that we do, which we probably won't get to today, which is too bad. But there's just too much chapter to cover before we're ready for the lab. Now, if you were looking at a mineral, and I meant to point this out earlier, remember that first slide had those big, beautiful red crystals. Did y'all notice that? Okay, that's, boy, I can't even remember what. Pretty complicated sounding name, beautiful crystal. Bright red. But most of the time, color is not the best thing to classify crystals with. Not very useful because it can be influenced by trace amounts of impurities. Have you ever heard anyone talk about brown diamonds or chocolate diamonds or yellow diamonds? Diamonds are clear, but just a little bit of a trace impurity can change the color of that diamond. Still a diamond, so color doesn't classify as a diamond. It's the other characteristics are more so. Okay? But color is the first thing we see, it's the first thing we notice, and quite often we try to use that to be our main classifier. Not the best. Streak is not telling you to do something they did back in the 80s. That was something way different. What streak is, if you take a mineral and you rub it across a piece of corundum or some other type of really abrasive substance, and when you do that, you're actually grinding it into a fine powder, then the color that you see of the streak, that is an excellent classifier. It is a color, but it's color of the mineral when it's finely powdered. So what they usually do, that's why they call it a streak. They rub it across thing, it leaves a streak. That will be a far more consistent indicator than color itself. Okay? So that's one thing they use. More than color is the color of the streak, the powder that's left over. Hardness is a very good tool. Okay? This is its resistance to scratching. Like if you had one of those crystals there and you tried to scratch it, your fingernail wouldn't work, the nail may not, glass might, but you found something that would. That narrows down the hardness of that material. Okay? There was a guy, and here's a potential paper topic, named Mo. Now this wasn't Larry and Curly's friend, this was a different one. And he came up with a hardness scale. Used 10 test minerals with increasing hardness. The number one in the list, the softest, was talc. Any of you, especially ladies, ever use talcum powder? Did you get any softer than that? Okay, but number one is a powder, but it's a very, very soft mineral. Going up to, anyone guess what the hardest mineral is? Diamond. Nothing will scratch a diamond, and a diamond will scratch anything else. Okay? So that's the hardness scale. There are 10 test minerals, and several of these will be on your lab. We're going to see some of them in the table right now. Okay, here they are. Number one, talc is the softest, followed by gypsum. Now, this is a pure mineral, but remember gypsum board or sheetrock, that substance that's in between the paper, you can scratch that with your fingernail, okay? It's not very hard. Now, that is a synthetic rather than a naturally occurring gypsum, but it's still about the same hardness. Okay, it's Maya? Is that right? Yeah. Okay. Know who you are before, there you are, okay. All right. So there's the next. Number 2, gypsum. Number 3, calcite. We will actually see some calcite. What I do, when y'all are doing the next lab, which is basically a computer lab, I will bring in with me several samples of minerals and rocks that I've accumulated over the years. Students have brought them, or various ways I've gotten those. And there is some calcite in there, and you'll see these. You'll read about it. It's going to be the first mineral you do on your lab, or number 1 listed. And it's a pretty impressive looking crystal, but is easily scratched. Fluorite. That's not one that's all that common. I can't remember if it's in the lab or not. And this is Cameron, right? Huh? Yeah, I thought so. Okay. Okay. It's next on the hardness scale. It's number 4. Apatite. Y'all remember that one? What do we get from apatite? Phosphorus fertilizer. Phosphate. That comes from apatite. Okay, that's the mineral that it comes from. That's number 5. Then we have orthoclase, which I don't think we'll have a sample of or any see. Quartz, pretty common one, and that's pretty hard too. That's sand, and we talk about sandpaper. That'll sand down just about anything except diamond and the things that are above it in the table here. Topaz is one of those semi-precious stones. I can't remember the color of it. Any of you know it's a yellow one. Okay, topaz is a yellow, beautiful semi-precious crystal, and it's quite hard. Corundum is also very hard. There are certain types of sandpaper that are not made of quartz but are made of corundum, and they will really polish just about anything, okay, except diamond. And of course, diamond is the hardest, and it is an incredibly hard. You just don't get anything. If you're wanting to cut through steel, use a diamond tip blade, okay? It will cut through just about anything, okay? Now, the hardness of some common objects, sometimes used for comparison rather than the actual test mineral. Like, I'm not sure I've ever laid hands on fluorite or orthoclase. Probably have, but didn't realize it. You know, they're not that common. But there are some common things that are, okay? And their approximate hardnesses are this. Your fingernail, that's a 2.5. It'll scratch gypsum, but it won't scratch calcite, okay? So fingernail is about 2.5. Copper, as in a penny. However, most pennies are not made of copper anymore, but it's approximately the same. That is about a 3.5. So that would be between calcite and fluorite. Okay, that's not made out of pure copper anymore, but it's got enough copper in it, it's about the same hardness. Okay, ordinary glass, that's the problem. You can have all different kinds of glass and quality of glass, so it's hard. But ordinary glass is either 5 or 6, somewhere in that range. Okay, since apatite isn't all that common, nor is orthoclase, that would be something you would use there. Your pocket knife blade, don't have one in the class, okay, no. That's again about a 5 to 6. Okay, so you see, you know that. Have y'all ever used a knife sharpener? Okay, I almost guarantee you that would be corundum on the knife sharpener, because it's got to be able to do metal. Okay, and since a knife blade is 5 to 6, see, it could be it's quartz, but I doubt it. Okay, corundum would probably be the material that you use to sharpen a knife blade, because you have to be able to polish away the edges of it. Okay, so there's your hardness. That's the Mohs hardness scale. All right. Other physical properties. Remember the crystal forms we talked about way back, or earlier last time? Related to the internal geometric arrangement of the atoms, 6 basic groups we already talked about. So basically, in your lab, you're really not going to do much on those. Okay? Now, these next two are related to each other. Cleavage and fracture. I doubt if many of you have ever seen a raw diamond. I haven't. You know, a rough diamond from in mine. Probably doesn't look all that impressive. But they have people whose jobs, and it's an incredibly highly skilled job, is to be a diamond cutter. Because nothing cuts diamond, okay? Nothing does. So you have to know just where to strike it to cleave it. Exactly where those planes are along which it naturally breaks into things. If you remember back when we did do those crystal forms, remember there were planes that are formed there. Those are the cleavage planes. What you see there, y'all remember the slide I'm talking about? It's going to race back. Okay, right there was one. Oh, there it is. There, well, it's right there. These are the cleavage planes. Okay, there. You know, those are the ones. If you strike it there, it'll break very nicely there. Okay. Here is the cleavage plane here. One right here. One right here. Those planes that you see here, those are the cleavage planes. That's where it naturally breaks. And that's what we're talking about here. Now, when we get to, there were some more pictures of it. These, where you can see that one? Isn't that really clear where the cleavage planes are here? Okay? Here's just a flat one. So those are your cleavage planes. Now, the problem is how to name these things. And what you'll find when you do the lab, they give you a series of numbers, and they don't tell you what the numbers stand for. A 111, a 101. Rather strange numbers, but that's describing in some sort of a system they have where they break. The tendency of a mineral to break along smooth planes. Now, as I said, these two go together. Fracture is the irregularity of broken surfaces. If you were to have hit that diamond in exactly the wrong spot, then you might fracture it. Okay? Now, for a diamond, it's going to take a pretty good hit to do that, but it can happen. And boy, just think of that guy. You know, that raw diamond is probably worth quite a bit, cut well. But if he fractures it, it's not worth much of anything except to put on a saw blade to cut through steel. Okay? No one's going to pay top dollar for that. So some minerals will cleave quite easily. Others you try to, and they do nothing but fracture, or it's very hard to cleave them, and they're going to fracture instead. So those two are going to show up together, cleavage/fracture. Okay? And when they do, I'll explain to you what you put on the lab. It's the irregularity in broken surfaces, where cleavage is the break along planes. All right. Luster almost sounds back like color and stuff, but it's not quite the same thing. That's the surface sheen. And there's many of those, not a huge number, but several. You can have vitreous, which is sort of water-like, metallic, which would be looking like a metal. There's metallic. Pearly, vitreous. Pearly would be looking like a pearl, not like a water. But there are others. That's the luster. Just the surface sheen of what that mineral looks like when you see the pure mineral. And then we get to density. Density is probably the very best indicator of what mineral that is. It's the mass to volume ratio, and as long as you have a fairly pure mineral, that's going to be the same no matter if you got a little bit of it or a whole bunch of it, okay? The density, the mass to volume ratio is going to be the same. Now, an alternative to the mass to volume ratio is a quantity called specific gravity. And all that is that this is the ratio of mass to volume, but once you have that ratio, you do that ratio to the density of water, okay? And then, you see, this is going to have units. Generally, kilograms per cubic meter, grams per cubic centimeter. It could be pounds per cubic foot or cubic inch or something like that. Most of the time we don't use that. This one has units to it because the mass is kilogram, volume is cubic meters or grams to cubic centimeters. But then when you take that ratio, kilogram to cubic meter or gram to cubic centimeter, divide it by the density of water, which is 1 gram per cubic centimeter or 1,000 kilograms per cubic meter, then the units go away and you have the same number you had if you had that in grams per cubic centimeter. And that's what they give it most of the time then. So if it doesn't have units, it's specific gravity. If it does have units, it's the density. Okay? Now, there's two factors, at least two factors that will contribute to how dense or low density the mineral may be. Number one is the kinds of atoms making up the mineral. Okay? If your mineral is largely quartzy, silicon, oxygen, that kind of stuff, pretty low density, because those are the elements that show up high on the periodic table. Okay? So the kinds of atoms making up the mineral. If you have much iron in the mineral, you're pretty low. That's going to be a high density most of the time. Okay? So it's the kinds of atoms that make up the mineral. But there's another factor, is how tightly those atoms are packed into the crystal lattice. There are certain types of packing that leaves a lot of space between. Those are going to be lower density. And there are other types of packing where just about every void is filled by another atom. That's going to be a denser than you would find in with the same level of atoms. If they're more tightly packed, then there'll be a denser crystal lattice. Okay. Now, that will definitely be one on the lab. Now, I'll explain this later, but let me say it now so you've heard it at least once. On your lab, the last column will say other. They've left off density altogether, and this is the best indicator, and they just will always give it, so that other is going to be density. And you can either use density with units or specific gravity without units, either one. But that will be your last column. And I'll say that over and over. I'll still, every now and then, have some students who will start filling in all sorts of other things there. No, that other is going to be density. Don't worry about that now. We'll get it with lab. So there's your physical properties. Now here's more on the physical properties, and these just show a little bit of it. This is a piece of naturally occurring mineral gypsum. Okay? Now just looking at this, you can see it comes across in planes. And you can see this person is taking his or her fingernail and scratching and making a mark on that. That means fingernail, which is 2.5 gypsum 2, yeah, indicates you have a low density, a low Mohs scale reading on that one. Whereas this is a beautiful illustration of quartz. Quartz is that tetragonal structure, and if you can see some quartz, you almost that shows them the minerals. These are good sized minerals too. They're very characteristic. Okay, that is hardness 7. Okay, this is hardness 2. Okay, just illustration of at least one of those physical properties, hardness. You can take your fingernail and scratch on that till the cows come home. You're not going to make a mark. You can take a nail and scratch on that, and you will not make a mark. Okay. Take a diamond and scratch on it. You'll make marks. Okay. So let's not. Okay. Or just give me the diamond. I mean, whatever. Okay. Now, that was our physical properties of minerals, which is pretty much what your lab will be for this chapter. Okay. There's a little blurb at the bottom of page 442. Grow your own. They're talking about minerals there, folks. Okay, never mind. Okay. I've tried doing labs with that, and they are messy, take forever, and I'm never very successful at them, so we're not going to do that in the lab. Okay. I tried for the first several years, couldn't get it done easily. Okay. Now, the example 17.1 in your text on page 443 gives an example that we could work. A 4.08 gram crystal. Let me back up and let's use this space here. A 4.08 gram crystal. Now, does anyone know what that's a measure of? I've mentioned it a few times. Did anyone pick up on it? Grams measures what? No. Grams per cubic centimeter measures density. What would gram measure? It's a 4.08 grams. Grams or kilograms always measure mass. Now, the thing with a number with it is your unit. The letter that stands by itself is your parameter. M, little m, stands for mass, and the unit for that is gram. Okay? A 4.08 gram crystal of the mineral augite measures 1.43, oh, this is a lot more involved than I thought it was, centimeters long by 0.098 centimeters wide, okay, by 0.89 centimeters high. Okay, there's your mineral. You have a single crystal that has those dimensions. This is obviously one of those. Let me scroll back real quickly. Whoops. Like I bet you it's somewhat like that. It's not a cube, obviously, because the lengths aren't the same, but it's either something like a rhombohedron, a prism. It's one of these. It's a very regular shape, like this, that, or that. Okay, very regular shape. So you can do a length times a width times a height, and that's what we're talking about here. Augite is I think it's an iron mineral. Let's see if we can find, yeah, there it is, a ferromagnesium mineral, okay? Doesn't occur that commonly, but you can have samples of it, okay? So here we have its thing. Its cleavage causes it to break into a rectangular solid with a length, a width, and a height. Its cleavage allows that. Now, the question is, what is its specific gravity? What do we need before we can do a specific gravity? You have to have a, Patrick, what was your answer before? Density. So you can name anything you want. I'll just call it capital D for density. There are other symbols they use for it, but density is what? Mass per unit volume. Okay? Now, usually capital V is volume. Little v is usually velocity. We're not dealing with velocities here, so that's a capital V. How do we get the volume of this thing? You have its length, its width, and its height. How do you get the volume? Multiply them. So someone pull out a handy-dandy calculator and multiply 1.43 by 0.98 by 0.89. you're going to get something, I'm guessing, about 1.3 or so. I'm just making a guess. What you get? 1.43 times 0.98 times 0.89. Second? 1.25. Okay, that was fairly close. So this has a mass of 4.08 grams, and what you say, 1.25? 1.25 cubic centimeters. You multiplied the numbers together, you also multiply the units, cubic centimeters. Do that division, and what do you get? I'm guessing about 3. Yeah, say again? 3.3? That's all the digits you got? Or maybe one more? Huh?
3.26.
Let's leave it at 3.26. Okay? Because you got 3 significant digits here, 3 there, 3 there. Oh, you only have 2, so let's leave it 3.3. Okay, sorry about that. That would be grams per cubic centimeter. But they asked for specific gravity, which is that density divided by water's density. And I happened to say what water's density was. Did anyone catch it? 1 gram per cubic centimeter. Now here's why that's true. When they were first coming up with the metric unit, they first came up with length, and they called that a meter. It was 1/10,000,000th of the distance between the North Pole and the equator when you pass through Paris, or something like that. Something that was based on the Earth, they came up with what a meter was. Well, that's a fairly large thing. It's about this long from the tip of my finger to my opposite ear. That's about what a meter is. Okay, that's pretty big. So they broke it into 100 pieces, and that's what made a centimeter. And then they took a little cube made out of centimeters. And by the way, centimeter is about the width of your little fingernail. Okay, so 1 centimeter wide, 1 centimeter deep, and 1 centimeter high. You know, that was like one of those tiny little sugar cubes that don't sweeten anything. Okay, they're so small. Okay, that would be a cubic centimeter. And they just said, well, we need a mass measurement. What's the most common material on the planet? Water, okay? So let's take water and say 1 cubic centimeter of water will be 1 gram of water. So that's why its density is exactly 1, because that's how they named a gram. 1 cubic centimeter of water has a mass of 1 gram. So when you divide 3.3 by 1, what do you get? Pretty hard math. 3.3. And your units disappear. So the specific gravity of that, and look at them, they did 3.26. Okay, let's go back. I'll let me talk myself out of it. Okay, 1.26 is the specific gravity of augite. And by the way, augite is an iron, like I said when we saw back the table there, ferromagnesium mineral, okay, meaning high in iron, so it's going to be pretty dense. Most of your densities will not be that great. Most of them will be in the 2 ranges, 2 to 2.7, 3.26, a little bit heavier. Think you will have one, I can't remember its name, maybe Galena or something like that, and it's like 4 or 5, really dense, okay? But most of them are going to be lighter than that, okay? And then the next example is just about like it. But that's a potassium feldspar, which is made up of lighter atoms than iron. And look at what its specific gravity is, 2.56. So you see that's more typical. So we'll see quite a few densities down in that range. All right. Now, any questions? Physical properties of minerals. Now, we move to 17.3, which is mineral forming processes. Okay? Now hang on to these concepts because you're going to see these in subsequent chapters as well, subsequent labs as well. These are some pretty important concepts that we got. How do minerals form? Well, formation of two liquid environments is the most common. Now, what do we mean by liquid environments? The first, of course, is dissolved in water. Okay? When you dissolve something in water, you can, and then evaporate the water away, you can wind up with some minerals. Have any of you ever put on the pot of water to boil that you're going to cook your corn in, and of course you add a little bit of salt, and you put it on the stove to bring it to a boil before you put your corn in, and then you got busy on the phone or something came up, you got playing a computer game or something, and you forgot about it. And you went back in later, and you had a pot there with what? Salt crystals baked onto the bottom of the pan. You can feel those crystals, okay? When you put the salt in, they dissolved immediately because you're heating the water. But then when the water evaporated, you had probably bigger salt crystals than you did when you shook them in to put them in the thing. Well, that's what we mean by water solutions. Crystals form from highly concentrated ions. Okay? Now, where would you get highly concentrated ions? Well, one place might be very deep in the ocean. Okay? Because things tend to settle out. And the further down you go, the colder it gets. And the minerals will come out of solution. Like I said, that salt dissolves real quickly in hot water. But have you ever gotten a glass of iced tea, but it's not sweetened, you wanted it sweetened, and you put sugar in it, and stir and stir and stir, and where does the sugar still land? In the bottom of the glass. And it's not very sweet. But if you were to take that same amount of sugar, the same amount of tea, but put it in hot tea, it disappears, right? Because the higher the temperature, the easier the dissolution rate, okay? The easier it dissolves, okay? So, deep in the ocean, where things tend to settle out, and it's very cold, there's where quite often crystals will form, okay? Water solutions, crystals form from highly concentrated ions, okay? That would also be the case, say, if you had pretty concentrated, and it can be any kind of solution, I'm going to say salty solution. It doesn't mean sodium chloride salt, any kind of salt. And then it's exposed and the water keeps evaporating, so the concentration of the salt gets more and more and more. After a while, it's highly concentrated ions with very little water. That's where crystals form. That's why I said when we tried growing crystals in the classroom, you have to boil the water, boil the water, boil the water, and if you get any contaminants in there, they don't form very well. So, and it takes a long time, and it makes a mess, and it's just not worth it. That's one type of liquid environment, water solutions. The other kind of liquid is liquid caused by heat. What does magma mean? Molten rock. Rock that has, molten means melted. Just put an E in here, you know, almost what the thing. Melted rock from which minerals can crystallize. Okay. How does rock melt? Deep inside the earth, the more pressure you have on top of it, the more friction there is, the more of those, and atoms are always moving. Molecules are always moving. If they're moving but there's a lot of friction between them, they get very, very hot. And the more pressure you have on top, the deeper they are, the more likely they are to melt. Think volcanoes, right? That's melted rock that has found a way to the surface, spews up. That molten rock, the minerals can crystallize. Now, this can happen below or above the Earth's surface. Surely when they come to the surface, they're going to cool very quickly and crystallize fairly fast. But if they're molten down here and have made their way up a little bit higher, but not reached the surface yet, then they can cool, but cool much more slowly. Okay? So they can happen below or above the Earth's surface. Now, magma, which is molten rock, wherever it is, if it reaches the surface, that's when we call it lava. There used to be a subname for this. It's magma that's been forced to the Earth's surface. Once it reaches the Earth's surface, it's called lava. While it's still below the Earth's surface, it's called magma. Okay? That's the difference. Now, the important factors here in both of these liquid solutions, okay? Important factors are temperature. I've already explained it to you. The higher the temperature of the liquid, the more it dissolves the minerals. The lower the temperature, the more likely they are to come out of solution. Okay? Pressure. The greater the pressure, then the more likely they will come out of solution. The less pressure, they may stay in there a little bit longer. And here's the big one, time. How long did it take for that magma to cool? Was it cooling very slowly, or was it cooling rapidly, like it came to the surface and then cooled really quickly? Okay? Time is important. And one of the other importance, the availability and concentration of the ions in solution. What ions are there, and how concentrated are those ions? Okay, those will both be factors in both of that, mostly in water solutions. Okay, now a lot of times when that lava comes to the surface and cools really, really quickly, the atoms, remember, one of the features of a mineral is that the atoms are in fixed patterns, crystal lattice. Okay? That's what makes the cleavage planes and those kinds of things. But what happens if it cools too quickly, then the atoms don't have time to line up where they're supposed to, and they solidify before they get lined up. That's what forms a glass. Rapidly cooled solid, lacking the crystal structure. Have you ever watched a glass blower do his trade? Pretty incredible, isn't it? Okay? What do? They take the quartzy crystals, and you see them. They're almost like a powder or something, but if you get them in your shoe, you realize that's just like a sand grain. It's quartzy crystal. Now, a lot of times they have color added to them. The color is not important. Remember, that's not a good way to classify. Anything can add color. Okay? But if they got just that quartzy crystal, and then they heat it up and heat it up and heat it up, and then they blow or do whatever it takes to make the shape, and then they make it cool quickly. Dip it in water sometimes, right? Or something to cool very quickly, and then you've got glass. You do not have a crystal structure. Now, I've heard some things that are contradictory about this now. I don't really know what to believe for sure, but that glass in the window was made just like we described. They heated up quartz, very, very hot, melted it, rolled it into sheets, and cooled it very quickly. That's what makes glass. If you were to break the glass, let's not, okay, you would not find nice, clean cleavage points. You see curves and all sorts of things like this. That's what happens, okay? Now, that glass is technically not even a solid. Looks and feels like a solid to me, but actually what it is, because there's no crystal structure there, those molecules can slide past each other. Now, I've heard this given as an illustration, and I've heard people try to debunk it. So I don't know which way to go on it now. They say some of the very oldest glass, say some of the very oldest cathedrals, or wherever you can find the very old glass in Europe, where they probably first started it stuff, you can go and actually measure the glass, and you'll typically find it's thinner at the top and a little bit thicker at the bottom. Not a great deal, but a little bit. Now, we live in a 1930s house. The 30s were a Depression time, and maybe the processes weren't as good, but you can tell which windows were original and which were not, because the original windows are a little bit wavy. When you see the light come through, it's a little bit distorted. Or you look out, things have that distorted pattern. Glasses have been replaced more recently. Very clear to look through those, and you know that's new glass. Now, whether that was the processes are better these days than they were back then, I don't know. Okay? But they say the movement of that is so slow. What would that be? 30, 80 years, you wouldn't notice that. So it probably was a process. Now, they say in the cathedral windows, they say the reason when you take those measurements is that they probably put the glass in with the thickest parts on the bottom and the thinnest parts on top. I don't know. I've heard it argued both ways. But glass technically is a super cooled liquid. Okay? Doesn't feel like a liquid, but it doesn't have the crystal structure that a solid would have. Okay. Oh.
Well, I guess it's so protein.
What's that?
I guess that's why it's so
Yeah,
protein.
and that's why it fractures easily. Okay, because it has no crystal structure. Are any of you Game of Thrones fans? I'm not. I've read the books, and the first one, maybe the second, and a couple of them were pretty good. The more he wrote, the worse it got in my mind. But anyway, a lot of people are just. I rode down to Montgomery with a bus full of mostly instructors and stuff, and there was a group of them that were sitting behind me that were just going over every episode in Game of Thrones. I thought, don't you have to like? Yeah, but I didn't say that out loud. Okay, but in that, one of the, if you had a sword made out of obsidian, huh?
Dragon glass.
Yes. Yeah. Well, is it volcanic glass? Yeah.
It's
Okay.
like the dragon eat up the rock.
Right. And then you could kill those whatever they were. So you are a Game of Thrones fan, aren't you? I thought so. Okay, go on and admit it. Okay. Don't you have a lot? No, I didn't say that. Okay. So if you've heard of obsidian, that is one form of a rapidly cooled glass. It's not actually a mineral. Okay? Now, minerals that were formed at high temperatures. That should give it away. These are usually from molten rock. Okay? Most of your minerals dissolved in water are not going to form at high temperatures because they stay dissolved. They form at cooler temperatures. So, Bowen's reaction series. There's another potential paper topic. Who in the world is Bowen? How did he come up with this reaction series? Who uses it? That kind of stuff. There's a couple of paper topics possibly in there. This is your silicate crystallization sequence. What minerals come out of solution at higher temperatures to lower temperatures? Your ferromagnetic silicates typically crystallize at higher temperatures. They can be very, very hot and still come out of the magma as crystals. Okay? Your minerals crystallizing later are progressively richer in silicon and poorer in iron and magnesium. So they'll be lighter weight because silica is lighter weight than iron, and they'll be lighter colored because silica is clear, iron is very black. So this is what we're about to describe is Tegan coming in. Okay. All right. Does anyone else come in since I called roll? I know they've been coming and going, but I think most people have been here the whole time. So this is what illustrates Bowen's reaction series. All right. Now, one thing I don't like about this illustration, they show the irons over here, and they say high temperatures here, low temperatures here, and they show the low irons here, the high irons here. These are going to be at way higher temperatures. They should be up here, and these should be down here somewhere. These are not equivalent temperatures, okay? These are relative temperatures, okay? But in your iron ferromagnesium silicates, your one that comes out of solution first is olivine. You don't find much olivine on the surface of the earth because it comes out of solution way, way deep where it's very hot. The only olivine you'll find on the surface are chunks of it that could have come up in a volcano that didn't melt in the volcano and came out as chunks, and later you find the chunk. That might be olivine. Most of the time, you're not going to see that much olivine. And it's very high in iron content. Boy, if you could have an olivine iron ore mine, you wouldn't have much processing to do. Very high in iron. Augite comes out next. We talked about that. That was an illustration we had. Hornblende next. Notice it's getting a little lighter, meaning there's more and more other things rather than like silica and other things. Because these are, remember, silicates. This is heavier in iron. These are relatively heavier in silica. More silicates than the iron part. Okay, hornblende next, and biotite. That's what we find mostly at the surface. The mineral iron at the surface is probably going to be biotite rather than olivine. That's going to be way, way deep in the Earth's thing. When we start talking about that, we'll find out that's the mantle. Okay. All I could think of was magma because I've been talking about it. Now come over to the non-high iron content, more siliceous materials, okay? The ones down here. Those that come out at the highest temperatures are your plagioclase, most of these are feldspars, okay? These are your plagioclase feldspars. Those are high in calcium content. They come out at very high temperatures, so they're usually going to be a little bit deeper. They're still silicates, remember. There's some iron in them, that's okay, but not a lot. Okay, you go down to the sodium plagioclase feldspars. Those are down here. And then you get into your potassium feldspars. I think those have their own name, orthoclase. Okay, I believe that is. And then you get muscovite, and finally you get quartz. There's hardly any iron, nothing but silica left in the quartz. This has calcium in it, that has sodium in it, that has potassium in it. Muscovite has some potassium and some aluminum. Quartz is just about pure silicon and oxygen. That's about all. Some impurities that make pink quartz or yellow quartz or other types of quartz, but the really pure quartz, clear as glass. Okay, that's what we use to make glass. Okay, so that comes out at the lowest temperatures, really near the surface. That's where you get most of your quartz. So the higher temperatures come out deeper, the lower temperatures more toward the surface. Now, it doesn't mean they come out on the surface. Those big, beautiful crystal quartz crystals that we've seen, those had to come out slowly because they got so big. Okay, so it was deep in the earth, but it was at low temperatures. Okay, and there's a picture of mine, page 442 in the book. Beautiful, beautiful crystal quartz. I mean, just absolutely gorgeous. Okay, page 442, figure 1710B. Okay. All right. Now, minerals formed at normal temperature. Okay? Most of these, like I said, are in contact with water, probably in solution of water. Formed at the Earth's surface in contact with oxygen, carbon dioxide, and water, and all those things will tend to interact with it. And these, guess what? There's your carbonates, carbon dioxide, carbon, oxygen, and usually dealing with water. Okay? And here comes Edward, right?
True.
Huh?
Yes.
Okay, good. All right. Okay. So the carbonates, presence of carbon dioxide, oxygen, and usually water. Sulfates, okay, those are sulfur, oxygen, the 8 mean oxygen. The oxides, obviously anything in combination just with oxygen. The halides, now they're in solution, so the water's involved, but really carbon dioxide, oxygen not too involved with that. The sulfides are sulfur and whatever else was there. None of the, well, probably in water solution. That would be it. Now, except for the oxides, these have substantially lower hardnesses. Okay, your sulfates, your carbonates, halides are all fairly low hardness, low specific gravities, because you don't have much heavy mineral in them, than the things formed at higher temperatures. Okay? Now, except for the oxides. A lot of those oxides will be iron oxides, which increases the hardness and increases the specific gravities. So that's why even the oxides formed at the surface, they're forming from, most of the time, from iron or something else like that. Okay. Now, if it's a lightweight oxide, like water, that's not a mineral because it's liquid, that certainly would not be high specific gravity or hardness. And now, the slide has this in it, and I haven't found this in the new edition of the books at all. They used to have a blurb on this, so don't get too wrapped up in this, but these are altered minerals. Evidently, they thought more about it in the past and are taking some of the emphasis off of it now. But just in case you ever run into it, exposure to different environmental pressures, someone leaving or coming? Must have been leaving. Temperature or chemical solutions can change minerals into new ones. Now, we'll see this when we start talking more about the rocks than about the minerals. Okay? It is important stuff, but they sort of have taken it out of the mineral side and moved it kind of toward the rock side. Okay? I would just suggest to you, let's just wait till we get to the rocks and we'll talk about how those do. Now, these altered minerals usually occur above 150 degrees Celsius. Now, that may not sound very hot to you, but remember 100 degrees Celsius is the boiling point of water. So you're another 50 degrees hotter than that. That's going to be quite hot. Look at this number. 2,000 atmospheres of pressure. That's a lot of pressure. Under what pressure are we right now, approximately? We have 1 atmosphere above us. So we're under 1 atmosphere of pressure. Did you know you're under that much pressure? Well, maybe later when you have all these testing, no, that's not the kind of pressure we're talking about. Okay? 1 atmosphere of pressure is about 14.7 pounds per cubic inch. Per square inch, PSI, per square inch. Now, a square inch is about the dimension of your two thumb joints put together like that. That's about a square inch. And if you think about how many square inches cover your body, multiply that by 15. That's a lot of force, weight on you. Why are we not crushed? Because our bodies are pushing out with more than that amount. Okay, you know they're pushing out because if you were to have a scratch, where does the blood flow? Out, not in. It doesn't suck in air or something else. The blood flows out. We're in greater pressure inside than what's on the outside because we're built that way. Okay, we evolved that way. We grew up in these environments, so we're there. Okay, now. People who do any of you do scuba diving? Have ever done any? I haven't either, okay? But people who do this, for every 10 meters that you go underwater, now 10 meters is pretty far. Like I said before, I'm about 2 meters tall. The ceiling would be just about 3 meters. So every floor of a major building would be about 3 meters. So 10 meters would be a 3-story building. So go to that part of the building, look at it from the outside, that's about 10 meters. If you go that deep in water, you have another atmosphere of pressure on you. Our atmosphere goes up thousands of miles, but because air is pretty light, but it does have weight, that gives us one atmosphere of pressure. Go down 10 meters underwater, you have another atmosphere of pressure. And then another 10 meters, another atmosphere, and then, keep on going. So to get to 2,000 atmospheres of pressure, you're way deep. Okay, they don't have water that deep. So it must be something heavier, denser than water on top of you, like all these layers of the Earth's surface, That's how you get that much pressure. That's pretty deep to get down there. That's where you start altering your minerals. And again, we'll talk about this more in the rock section. But remember that picture they had really early in the chapter where you had that big old rock there and it had all these layers that were all bent and twisted and things. I said that's one of the oldest rocks on the planet. That was altered big time. Okay, those minerals changed over time by the type of rock that was. And here are some. Garnet is another one of those semi-precious minerals. Is that one red? I don't know. Okay, that one's red. I don't even know what epidote is. Do you? Okay, epidote, I don't know. Talc, boy, as soft as that is, I wouldn't think that's too altered, okay, except maybe chemical solutions have altered it. Graphite, another really slick material, and serpentine, which is an asbestos source. We'll talk about this a little bit later in another chapter. There are a lot of asbestoses out there that are not harmful at all. But if it has the name asbestos, people keep it far, far away. There's only one really type of asbestos that's really harmful, but people can't distinguish them easily, so they stay away from asbestos altogether. I can't remember if serpentine's a bad one or not. Okay, but these are altered minerals. Okay. Then we get to our ore minerals. And again, this doesn't show up per se here, though there has been mention of it earlier, back when we did the classification of our silicates, non-silicates. It was a non-silicate ore mineral. These are mineral deposits with economic value. Okay? Yeah, we're familiar with that in the Birmingham, Bessemer area, aren't we? Because iron ore, but not just iron ore. Calcium carbonate, okay? Limestone. I wouldn't be surprised if we wouldn't have a little bit of bauxite, perhaps, in the area. So there could be a variety of minerals here. Usually when there's some, they're often found in veins, which means layers or streaks that occur inside other rocks. These are usually thin, flat bodies of the mineral material. That's what the veins are. I don't know why they put it in a different bullet. They're left over from the crystallizing magma and flushed away in hot water solutions. That bullet doesn't make a lot of sense to me, but I think I know kind of what they're talking about here. When things form, if the condition stays the same for a long period of time, then the same stuff is going to come out of solution altogether. And that's what I think they mean there. When you're crystallizing magma, if things are happening rapidly, everything crystals out there, okay? But if it's changing temperature very slowly, the things, remember that graph on Bowen's chart, okay? The things here are going to all come out together. These will come out together. So this is why those thin, flat bodies were formed. They came out very slowly, but you had pretty pure, concentrated types of crystals all together, okay? And it could, other stuff could be flushed away by hot water solutions, usually leaving that behind. Now here's some examples, and I don't see why this one's in here particularly, but we talked about it earlier, so it's good that it's here. Pyrite is iron sulfide. Now I don't count that an ore mineral. I don't know why it's listed here, but that's called fool's gold. That settles out in a certain area, and people, hey, we've hit gold, look at this, it's beautiful. And it is beautiful. It's just not dense enough for gold. That means it's fool's gold. Iron sulfide pyrite. Chalcopyrite, which is a sulfide again, but this is copper and iron. You would think with calco that means calcium. It doesn't. That means copper. Copper pyrite. Pyrite, iron sulfide. This is copper, iron, pyrite, sulfide. Okay, I don't know why they mentioned that in particular, but it is. Now, let me just go back and make sure of something. No, that's right. Okay. I was thinking that may have been one of the minerals they listed before, but it wasn't. All right, we're through with the first part of the chapter, which is the mineral part. Okay, we're going to move now into the rock part. This is 17.4 on page 444, and this is sort of the other half of the chapter. I'm not saying it's divided evenly in halves, but the title of the chapter is Rocks and Minerals. We did minerals first, and now doing rocks. And here's the reason. Because rocks are made of an aggregation, meaning a mixture of coming together of one or more minerals. So you have to understand what the minerals are first, one or more minerals, and perhaps some other materials. So to be a mineral, there are very strict criteria of what you could be, okay? Naturally occurring, non-organic, crystal structure. Rocks don't have to have those. Sure, they've got minerals in them, but they can have the other materials as well. And we could have Chris here as well. Okay, there he is. All right, how are we doing on time? Okay. Okay, so that's what a rock is. An aggregation of one or more minerals and perhaps some other materials in them. And we'll see some examples of that. Minerals are physically combined to make rocks. Now what? Sure. But what's the key word here? Physically combined. Remember when I gave the examples of sodium, chlorine, making sodium chloride. Okay, that's a mineral, halite. Sodium and chlorine, sodium an explosive soft metal, and chlorine a poisonous gas, combine together to form a white product we eat, put on our food to make it taste better. Hey, it has nothing of the same nature, characteristics of either one of the components. But rocks are minerals that are physically combined, not chemically combined. When you have a chemical reaction, everything changes. All the characteristics, everything else. When you have a physical combination, it just sticks together. It's still quartz. It's still augite. It's still biotite. It's still hornblende. It's whatever it was that just physically stuck together. Okay? That's what a rock is. It's a aggregation, not a chemical process. It's just a physical process sticking them together. Almost like gluing, but not, well, very close to that. Most rocks are, guess what kind of minerals? Silicate minerals. Remember, 92% of the Earth's crust is made up of silicate minerals. So most rocks that you find in the Earth's crust are going to be made out of silicate minerals. No big surprise here. Now, we classify rocks a little bit differently from how we classified minerals. Okay? They're based on how the rocks were formed. Three main classification groups: igneous rocks, sedimentary rocks, metamorphic rocks. Does anyone know what igneous means? If I were to cover this and ask you to put in 3 more letters and make a word, what word would you make? Ignite, which means burn. Okay? So igneous rocks are rocks that were once liquid, once magma. Okay? They are formed from molten material. That's what an igneous rock is. It came from a very hot source, molten rock. Sedimentary rock is what I feel like on a Saturday afternoon. No, not. Okay. Sedimentary are things that have settled out. And usually in layers, not always, usually in layers, they form from other rock fragments, okay? Or chemical fragments, you might say. That's sedimentary rock. Other rocks that are broken down and then reformed into rocks. And then metamorphic rock. Did any of you ever read, I haven't read it, but I don't know if it's a short story or a short novel or something by, goodness gracious, what was his name? Weird writer, German, I believe he was. But it's Metamorphosis was the name of his novel. And it basically was a guy who had been really obnoxious his entire life. And he woke up one morning and was a cockroach. Okay? Pretty appropriate, huh? And goodness, I can't think of the guy's name that wrote that. But that was Metamorphosis. He changed to something very different. Okay? The more classic illustration of this is what? But yeah, a hairy little caterpillar, going into its chrysalis or whatever you call that, and then emerging as a beautiful butterfly. That's metamorphosis. Okay? If any of you are into the scriptures, Romans 12, 1 and 2. Transformed, changed, metamorphosis. Okay? Metamorphosis. Something that was something else changed to something completely different. That's what metamorphic rocks are. And we'll get to the differences later because each one of the next several sets of slides is going to talk about each one of those. So let's start with igneous rocks. Okay? Igneous rocks were all formed from magma, either above or below the Earth's surface. What is magma called when it's above the Earth's surface?
Lava.
Lava. Okay? Below the Earth's surface, it's just still called magma. That's all. All rocks were at one time igneous rock. Sedimentary rocks, those fragments, mostly came from igneous rocks. Metamorphic rock, before they metamorphosized, a lot of them were igneous rocks. Okay? All rocks were at one time igneous rocks. Because guess what? We started as a molten ball of fire, basically. So the Earth was formed as one big chunk of igneous rock, basically. And then things started changing. Now, we've been talking about cooling, and we talked about time, temperature and time. Put those together and you get the cooling rate. The cooling rate determines the texture of the rock. Okay? Cooling rate determines the texture of the rock and of the minerals too, by the way, but we're talking about rocks now. So let's talk about two basic classes of cooling rates. The intrusive, in means inside the earth, okay? Intrusive igneous rocks, those are formed inside the earth, beneath the surface. Those are usually slow cooling process, and they produce large crystal size. Remember that beautiful chunks, those crystals of quartz we were seeing? Had to be pretty deep in there to be a very slow cooling rate to form very large crystal sizes. Okay? Slow cooling produces large crystals, mostly from intrusive, formed inside. The rocks it make are then coarse grained. You rub your hand over that basic rock, it's going to feel rough. You look at it and you see crystal, big visible crystal faces there. The cleavage planes, you see pretty big ones. Okay? Whereas the other ones are extrusive. They've exited the Earth's core, or the Earth's interior, and have made their way to the outside, formed from now lava, because all igneous rock came from magma. Now this is coming from lava on the surface. That rapid cooling produces very small crystals. Very small crystals. You look at that, you feel of it, you don't feel as big a chunks, as much roughness. You also look at it and you can just barely see any crystal faces at all. You got to get a magnifying, that's on here, because they're very, very small crystal sizes. Okay? Anyone know what this is? Oh, excellent. All right. 3 extra points, -5. Okay, never mind. Okay. All right. It's granite. Here's what makes it granite. 2 major things. You do see little bits, if you look carefully, of darkness in there. You see there, a little darkness there. There's a little bit of an iron crystal in there. Probably biotite or something like that. But most of it is whiter or lighter color. The whiteness is probably quartzy type material. The sort of brown in between would be some of your plagioclase or other things like that. So it's made up of a number of different minerals. But if you felt of that, you can almost see it. It's rough. And if you looked at it carefully, this picture isn't particularly good, you would see individual crystal sizes. Typically, granite is large crystal size, meaning where did it form? Interior, yeah. The large crystal size, coarse grain, means it's slow cooling, it formed inside the earth. Intrusive igneous rock. Okay? Go to the other extreme. And here we have obsidian. Okay. This has not been made into a sword, by the way. Guess what the chemical composition of these are? Almost identical. Does that look anything like that? No way. This was same chemical composition, but cooled very, very rapidly. Not even so you form small crystals. This is a obsidian, which is a glass. It cools so quickly that it didn't form even small crystals. So it has this glassy sheen to it. There's the luster. That would be a vitreous luster. This would be something else. I don't know what luster you would call that. Okay, but this would be very shiny, glassy type of structure. In fact, I think that's one of the lusters is glassy too, which is similar to vitreous. So same material, looking quite different, characteristics quite different. Large, coarse crystals, no crystals. Okay. Now, in between, you get other materials as well. We'll see a table with that coming up really soon, as in close, really close. So here's our igneous rock classification. Okay, we had intrusive, extrusive, that was one class. Here's some more. Two factors. One is mineral composition. We talked about this before. Those formed deeper are typically going to be higher in iron. Those that formed at cooler temperatures are going to be more siliceous. Texture, again, those formed deep, usually large, coarse crystals near the surface or at the surface, fine crystal, if any crystal. Okay? So, now what this is talking about is a table. I haven't shown the table yet. Here's a table. Okay? Two factors mineral composition. The right side of the table is high in calcium, iron, and magnesium. Now, why they wrote it as CaO, FeO, and MgO is a mystery to me. Okay? Yeah, they could be oxides, but it's just iron, calcium, and magnesium. Ca is calcium, Fe is iron, Mg is magnesium. Why they put those in there, I'm not sure. Okay? But these are the darker colors, heavier, denser materials, especially the iron. There's your olivines, remember? Way down deep. The first thing to come out in the Bowen thing at the highest temperatures. These are all ferromagnetic over here. They throw in a couple of other names here they didn't mention before, pyroxene, amphibole, but there's biotite, that was the iron that came out last, okay? And that's getting a little lighter color, these are the darker color, a little bit lighter colors, and getting more siliceous content, silica content, this had less, okay? So that was mineral composition. More irons this way, more silica that way. Okay? Textures, that depends on where it was formed. And you don't see it here, you see it up here. These are coarse textured. Granite, light colored because you're down in this. You got little bits of biotite and maybe amphibole in your granites. That was that little bit of black that you saw there. Then you saw your plagioclase and your feldspars. They were in the middle, so the brownish kind of colors. And then you had the quartzy, which were white. This is almost totally silica here. Okay? This is still higher in silica than you are over here. Now, that was coarse grain. Fine grain, same chemical composition, very similar to the obsidian glass, but this is fine grain, not without grains. This is rhyolite. Same composition, correct, but this happened at the surface. And why we don't see more rhyolite, I don't know. Maybe it just breaks down so easily and then forms something else. I don't know. But then your medium darkness, medium density, all that, diorite and andesite. And again, I'm not sure I've ever seen either of those. But then you get back here in the high iron content, gabbro, the countertop we have a 2-bedroom bungalow over in Georgia on the farm where I grew up. When my parents died, that was split up, and so we built a little place so we could stay when we need to go over, like I have to go over this weekend. We have a place to stay there. That's made out of gabbro. You can look at that and see the large crystal faces, those cleavage planes, big old crystals there. You can see it. Whereas, and I've got samples of this I'll show you when we do the next lab, is basalt is the fine grain. Now, typically the basalts are formed at the bottom of the oceans. Because guess what? The bottom of the ocean is pretty cold, wouldn't you say? Way down there, a long way from the sun. Okay? Pretty cold. And yet you have volcanic activity down there. And when that magma comes to the surface, guess what? It cools very quickly in that cold water. That forms basalts. And we actually have basalt deposits way up in Montana. You think, how did they get there? Well, that was one time the bottom of the ocean. The Salt Lake, Great Salt Lake, that's a little puddle left over from the ocean. retreated. You know, weird what's happened on the surface, how things have lifted and sunk and done other things. The salt we have in our master bath in our house here in Birmingham, I'll bring samples of that because there were some that broke up, and I grabbed them and brought them in here. Okay, fine grain, coarse grain, fine grain, coarse grain. High silica content, high iron content. Okay, so that's what they mean. Mineral composition: right hand more iron, left hand more quartz. In between, kind of a mix. Non-ferrous composition on the left of the figure, because the ferrous came out at high temperatures, it's long gone. These are lower density, no iron, lighter in color, no iron, more silica. The granite is the most common example on this side. Coarse grain, because it happened, came out of solution. It's a intrusive igneous rock, meaning it came out so it has coarse grain. The rhyolite, which you don't see that much of, that was the fine grain. Okay? The ferromagnetic composition on the right-hand side, greater density because of the iron, darker color because of the iron. Okay? Example is basalt here, but the reason it's basalt, more volcanic activity under the ocean than you have on the surface, because there's more ocean than there is surface, and that's where most of the basalts were formed. Fine grain because they cooled very quickly, but high iron content because it came from really deep. Okay. We'll see examples of both granite and basalt in the next lab. All right, so the next lab, you'll be doing on the computer all your physical properties of minerals, and at the same time I'll have the actual minerals for you to look at and play around with and stuff. All right, that was igneous rock. Where does igneous rock come from? All igneous rock. Magma, exactly. Whether it's on the surface or below the surface, it came from magma. The sedimentary rock, on the other hand, were formed from particles, remember that, or dissolved minerals, remember that, from previously existing rocks. Okay, they don't say what kind of rocks. They could have been igneous rock. They could have been other sedimentary rock. They could have been metamorphic rock. They just came from particles that were left over after they weathered away, broken off, whatever, or they dissolved away in water or in acids or in other things. So, the particles, well, okay, we're starting to get to the sediments. Let's start with that. Sedimentary rock came from sediment. Those are accumulations. Now, these are talking mostly about dissolved materials, not completely, but mostly. Silt, sand, and other materials that settle out of water. What's the difference in a silt and a sand? Does anyone know? Particle size. That's all. Okay? Now, I have on me a dime here. Okay? Dime to my name. Okay. If you took 2 dimes and put them together, I only have one. That's going to be about 2 millimeters. Anything that's about 2 millimeters, maximum dimension, that's going to be a sand particle. Okay? Silt particles are much finer than that. And even finer than that would be clay minerals. Let me tell you what the clays get down to. I think I've said this before. Take this dime and slice it. If you can imagine this, I don't think you can physically do it. Slice it into 1,000 equal slices. That one thin little dime. 2 of those slices put together would make the largest clay particle you ever would find. Can't even imagine. You cannot see a clay particle through an ordinary microscope. You have to go to an electron microscope to see a clay particle. Okay? The silts are in between. Now here's the way I think of it. Feeling. If when you rub this material between your fingers. If it's the sand, it's going to feel gritty. That's the sand. If it feels like flour or dust, that's the silt. And if it's way too small to even see, that's clay. Okay. So that's what make up some of these sediments. You can have other materials that settle out of water. That could be gravel. That would be chunks of things far bigger than 2 millimeters, 2 dimes together, and other things as well. Now, if they're made up of the particles, these are called clastic sediments. They call them particle sediments. I don't know. They call them clastic sediments. Okay? Accumulated from either rocks at various stages of breaking down. Every rock out there, igneous rock, metamorphic rock, sedimentary rock, weather is happening to it, things are grinding against it, they're breaking down. Always, it's a continual process. Anything that are particles that came from rocks, these are your clastic sediments. If that's where the thing that made your sedimentary rock was a particle from a previous rock, that's a clastic sediment. So here, now this table shows up about 3 or 4 times here, so get used to it. We're only looking at this part right now. If it's larger than sand, that would be classified gravel or something like that. Then you have conglomerate, the rock, the sedimentary rock that formed from the clastic sediments that were larger than sand grains, would be conglomerate or breccia. Okay? Now they're going to show a picture of this in your book. And I've sort of not kept up with turning my pages here. Here we go. On your page 448, the breccia is sedimentary rock formed from consolidation of large angular fragments into solid rocks. Okay? That would be breccia. If they're rounded, not angular, then it would be called conglomerate. Okay? So let me get caught up with where we are now. Page 446, I failed to mention this. There's a nice little blurb, takes up probably more than half a page, on the cost of mining mineral resources. Okay? You might go to some of the mining companies around here and find out what they think of it, but it's well worth a read. Okay? Then Amanda's piece of obsidian is down here at the bottom of that page. There's a few examples given here, and actually example 17.3 refers to that. Let me go back. This right here, and based on the percentages they tell us, you try to figure out where you are in there and what kind of rock it is. It's really a fun example to do. Okay, we probably should have done it, but I forgot about that. Then table 17.3 is this table right here, 17.3. It's green in your book, it's brown here. Okay, so that's conglomerate or breccia. Larger than sand particles, in other words, gravel particles, and if they're rounded, it's conglomerate. If they're angular, it's breccia. Okay, if you have sand particles, that's 2 dimes together or smaller, that gritty kind of feel, that's called sandstone. I have several examples of sandstone you can feel, handle, and stuff in the lab next time. Okay? If the clastic sediment made out of particles, these particles are either silt or clay, that fine powdery looking stuff or feeling stuff, that would be siltstone, claystone, or shale. Shale is made out of clay particles. Shale forms in sheets pretty much. And it's you don't feel any grittiness about that. It's a sedimentary rock, absolutely no grit, and it forms in sheets. We'll talk about that a little bit later too. Now, we're going to get to the chemical later, so let's hold off on this. You'll see this slide several times. These are your clastic sediments, these up here, made out of particles. Big particles, medium particles, small particles. Okay. Now, let's break those particles down a little bit more, okay? The clay, and they say, or dust, they say the same thing for silt. You can't really tell unless you look with a microscope. If you can see it through a microscope and see the actual crystals, that's silt. Electron microscope, that would be clays, okay? And it gives those particle sizes, but these are just fractions of inches or millimeters, and it's really hard to imagine. So think of slicing a dime. Claystone, siltstone. Now, I'm not absolutely certain about this, but I have a gut feeling it's the same type of stuff. There is a company that makes wood-burning stoves, and they make them out of what they call soapstone, and that is so slick it almost feels like it's soapy, but it's not. It's actually a thing. That to me has to be a claystone. Now, I don't know. I've never seen anyone describe it, but that has absolutely no grittiness to it at all. So I would think that it was either siltstone or claystone. I'm guessing claystone to be that slick feeling. It's actually a stone, but it feels almost like it's soapy. Okay? Here they tell about conglomerates. Conglomerates are rounded fragments. Breccia have angular fragments. Okay? Now, both of these are also known as mudstone. That means no grittiness to them at all. Shale, if it splits along the parallel planes. And here we go with Maurice, right? Okay. So now we're only missing Lexi, Latricia, and Samaya. Okay. Now we may have lost a few. There's been so much coming and going, I haven't kept up, but all but 3 have shown up today, which is very good. Which those 3 have shown up. Okay. So this breaks it down into the actual sizes as opposed to slicing dimes and stuff like that. You can have actually boulders. I don't think boulders form into other rocks. Okay, they just remain their own rocks. Okay. All right, that was table 17.4 in your book. Again, green in your book, brown on the slide. Okay. Now I think we're ready for the other kind of sediments, not the clastic, which are particulates, but chemical sediments. Now, what we mean by a chemical sediment is a sediment that one time was a rock, but it's been dissolved away. Now, how is it dissolved? Well, sometimes water is enough to dissolve away parts of a rock or mineral. Okay? Other times it might take a little bit of acid or other things like this. I think I've asked this question before, maybe not. I ask it in every physical science class. Have any of you ever been to Yellowstone? Okay, you have. Isn't that one of the most incredible places on the earth? Not just in the U.S., on the surface of the earth. It is unbelievable. Some places smell so incredibly horrible because of all the hydrogen sulfide and sulfuric acid and things that are coming up. And some of those, they just have geysers everywhere. They have paint pots. They have just all sorts of geological features just showing up. It's a big park. You can spend days in that park, but there's so many features there. You just drive a little ways, you see something else. Okay? Incredible. Well, some of those, like I say, hydrogen sulfide, that rotten egg smell, the sulfuric acid, not too far from that. There's some really, they tell you, stay on the boardwalks. If you step off of those, you may find yourself in your foot being eaten up with acid. Okay? You see buffalo who have been eaten up with acid. Okay? There are all sorts of things. So it's not just dissolving from water. Sometimes you have some pretty harsh chemicals that are bubbling up from somewhere deep in the earth that can have some pretty strong dissolving characteristics. Okay? There are three sedimentation paths of these chemical sediments. Okay? One is chemical precipitation from solution. Now, what do we mean by precipitation? What do you think of when you think of precipitation? Rain. Well, this has nothing to do with rain except that it falls out. That's what precipitate means. It falls out. Rain falls out of the sky, it's precipitation. If you were traveling in the mountains somewhere and actually fell into a crack, that's sometimes called a precipice. You precipitated down the precipice. You fell down the precipice, okay? That's what we mean by precipitation, okay? I took chemistry my first quarter, freshman year, when I went to Georgia Tech. And the very first lab we did was they gave us some solutions, clear liquids, okay? And let's see if I can get this right. I think it was silver nitrate, I believe is what it was, okay? In solution, it dissolved because nitric acid is a very strong acid that formed a clear solution. We dropped some, was it just sodium chloride in it? Or something, pretty simple something in it, another clear solution, and all of a sudden stuff started falling out. That's called a chemical precipitant, because even though silver nitrate was soluble, silver chloride was not. And so when you put the sodium chloride solution in it, suddenly your silver chloride came falling out. That's called precipitation. That's a chemical precipitation, something falling out of solution. So you have something, high concentrations of stuff dissolved in water, dissolved in whatever it's in, but then it runs into something also dissolved in water that now the things won't hold together. They won't stay dissolved. They precipitate out. So that's one path for your sedimentation. Something that was in solution now precipitates out of solution. Chemical precipitation. It mixes with something else that will not stay dissolved, and it comes out of solution. Okay? The second is one that I mentioned before, crystallization from evaporating water. Okay? Now, we don't have this here, but if you go out west, especially in some of the more desert-type states, you will see sometimes a white film on the ground. Not much grass growing or anything else, just a white, sort of powdery-looking something. What that is salts. That water has come to the surface, evaporated, and left the salts behind. Here we have so much rainfall, the salts get dissolved and carried into the soil. Out there, they get brought to the surface by the water, and then the water evaporates, and you get salt built up on the surface. Do any of you have plants at home that you either raise or your mom or somebody raises and stuff, and they're in clay pots, and after a while the pot will get sort of a whitish look at that? Water is actually seeped through the pots. You don't see it, but then evaporated, leaving the salts behind. So that's what we mean by crystallization from evaporating water. It can be done anyway. So either it's chemical precipitation by two different materials coming together and it won't stay dissolved, or crystallization from evaporating water. And then the third kind is what we just classify as biological sediments. Now that comes close to, okay, let me say this. This obviously is not a mineral, is it? If it's biological sediment, that came from living organisms. But they can be in rocks. Remember, when we first identified rocks, it said made up of one or more crystals and other substances. So biological sediments are perfectly legal to find in sedimentary rock. In fact, you do that quite frequently. So that's the other feature, sediment paths that you can find in a thing. I wouldn't call that a sedimentary path, but I guess they had nowhere else to put it, so they put it here. All right. Recognize this slide? Okay. We've done the first half of it. Those are your plastic sediments. We've already seen those. now your chemical. Okay? One type of chemical sediment is calcite. Calcite is calcium carbonate. Now, before I was calling it limestone, the book called it limestone. It's really, calcite is the mineral that makes up limestone. There's other things in limestone besides that, but this is one of the minerals. This is the chemical that came out of solution, calcite, and made up limestone. Now, I didn't know this until I had a student in this class bring me something. That calcite forms, anyone have a clue where it might form? It was a complete mystery to me. I never would have guessed it. In the coal mines. Whenever you have coal, sometimes you'll have this layer right next to the coal made up of a whitish kind of crystal that's calcite. There's something about where the carbon comes out here, the calcium carbonate comes out there, okay? And you'll see samples of that because he brought me some, okay? So that's what calcite is, the main mineral in limestone. Another chemical sediment is the mineral there is dolomite, and that comes out as dolomitic limestone. They call it dolomite there too. I'm guessing they have some up in that town, just a guess, but they must have dolomitic limestone. That's a mixture of calcium carbonate and magnesium carbonate. As I said before, that's the kind of, if you ever need to reduce the acidity of your soil, use dolomitic limestone. It's not as fast, but it adds valuable magnesium to your soil with calcitic limestone. Another one is gypsum, is the mineral, and they call the rock gypsum too. Well, obviously if it's rock, it has other things in it too, but it has that. That's calcium sulfate is gypsum. Another chemical that comes out of solution, this is probably from evaporating water, halite, sodium chloride, salt coming out of solution. That's probably in here. Okay. Now, here are some pictures. You have others in your book that are fairly similar to it, but this is a piece of limestone, and it has probably calcite in it, other minerals, almost certainly some silica, okay, because, you know, formed in sand type thing. But what do you notice down here? Anyone recognize this? Anyone see it clearly enough? A little seashell. That's the biological sediment. That's not a mineral, okay? It's not inorganic. That was very organic, but it just happened to form. Well, that's where limestone forms. It forms at the bottom of the ocean as the chemicals come together. The calcite, the dolomite, other minerals come together, and always at the bottom of the ocean you're going to have seashells and other fragments of organic stuff, and that can get lobbed up in the rock, the sedimentary rock. Chemical sediment, okay? Now, this is a piece of sandstone. Now, we'll talk about this later in other chapters too, but notice how you can see the layers. Now, the layers probably came out of solution flat, horizontal layers. Later, something happened that bent them. Pressures, we'll talk about this in a later chapter. That's why you see the bending here. But originally, those were flat. These things came out, then that layer, thin layer came out, then this one looks up much more like that, then another one that looks like this, but then a lighter layer came in, and then you got a darker layer again, so it came out in differentiated layers, and over time, and we'll talk about this in just a few minutes, how this formed, okay? This, any idea what you would call this? We mentioned it earlier. That's certainly not sand or silt or clay. This is breccia. Look at the angles in that thing, okay? So this isn't rounded. This is gravel in a sedimentary rock. This would be called breccia. Okay, very good. This is your chemical sediment. These are both plastic sediments, sand and gravel. And here's that same figure again, table again. They love that table. They stick it in every slide they can find it. Same like saying before. This is chemical limestone. Okay. This is sandstone, plastic right here, and this is breccia. This one up here, plastic. Okay. Make sense? All right. Now this is sometimes the point at which people ask if they need a break. Do we need a break?
Yeah, we're not anywhere. I mean, I was just waiting to see if you got to a stopping point. Is this a good stopping
What's that?
Is this a good stopping point?
This is as good as any. I just knew about this time you usually ask for one. You want one now or go on?
One now's good.
Okay.
It's been 2 hours.
All right. Not a bad time to stop. We are getting fairly close to the end of the chapter, but not quite there yet. So let's take a quick break. Try to keep it 5 minutes or less. I've got to run something down to the copy. All right, we're not going to get started yet, but I just thought I'd put this paid political announcement out here. I mentioned this last time, but I want to keep harping at it because I really need these things in. I have received first uno research paper. Okay, we're moving right along with the term here. This is a mini term. We don't have that many weeks. We're in the 3rd week right now. That means we're about a third of the way through the course. And I don't have a third of the papers in, so please don't forget about your papers. Okay? Number 2, your labs. The first lab, I'm still missing 1, 2, 3 of the 4 from people who have been here. The first test, I'm still missing 1, 2, 3 from people who have been here. Lab 2, missing 1, 2, 3 from people who have been here. It's not always the same 3 people, but sometimes it is, okay? And test 2, I'm still missing 1, 2, 3, 4 from people who have been here. So most of you have been getting everything in and then pretty reasonably. But please, folks, if you're missing labs or tests, make arrangements, get them done, get them into me, please. I'm having to carry around all this stack because I can't return anything to you until I get them all in. So please get your labs in. Okay. That was my paid political announcement. Okay. Didn't get paid too much, though. All right. Now, any questions or anything we've done so far? All right. Remember when we were doing igneous rock, we said where it came from. Where did igneous rock come from? Magma, lava, okay. And then how it was formed. It was either formed inside slowly or outside rapidly. Okay, intrusive or extrusive igneous rock. We have various classifications. Well, we've talked about where sedimentary rocks come from, either particles broken off from other rocks. Those are called what kind of sedimentary rocks? They came from particles. Remember our second? It sounded like plastic, but it wasn't. Plastic, oh, of course, okay. Plastic sedimentary rocks, or it came from chemical sediments, which were called, what were they called? It's a trick question. Chemical sedimentary rock, okay. Plastic or chemical. So, but we haven't said how these form yet. So here is lithification. When you see the prefix lith, or litho, or something like that, think rock, okay? So this is the rock forming process. Lithification, the rock forming process. 2 main parts. Now this is primarily sedimentary, plastic sedimentary rocks. primarily. Okay? The first part is compaction. These pieces, the resin, the chunks, the sand, the whatever it happened to be, got sedimented. Okay? Sedimented. Layer on layer on layer. And as it goes layer on layer, these layers down here get compacted. Tighter and tighter together because all the weight above them. Okay? So that's the first thing. Compaction. Reduces the thickness of the deposit, squeezes out the water. Because most of the time, water is delivered this. Not always, but most of the time it has. And it's very important that water is delivered. Because water is a good transport mechanism, but it's also, water dissolves things. Remember, that's what it does so well. It's a good solvent. And when the water gets squeezed out, sometimes the material that's in the water gets left. And that contributes to the second part. Cementation. The spaces between the sediment particles, which have gotten smaller and smaller because they've been squeezed from all that pressure from above, get filled with chemical deposits, mostly left over from the water. Okay? And as the water leaves, the chemicals get more active, and these chemical deposits binds the particles together. Okay? Now we have learned from that, I don't know if it's actually sedimentation, but that's exactly what we've got here, isn't it? What we do, we get particles, sediments, mostly cement, which is calcium oxide, calcium carbonate, maybe a little bit of gypsum or something like that too. Mix it with water, compress it together, squeeze out some of the water, let the water evaporate, and that forms the cementing agent that holds the blocks together. Okay? Yeah, that's the same type of thing, only on a lot slower scale than what these blocks were put in. But that's the process that happened. So here's the diagrams of this. They go to a special thing saying, and I think this is totally backwards. I would say the white ones here should be the quartz, the sort of colored ones the feldspars, and maybe these are biotite or something else. It doesn't matter. But different chunks, fragments of broken rock, okay, classic sediments, they get deposited, okay, usually by water. So usually there's water in between in the pore space here. But then more get put on top and more on top and more on top, pressing, compressing, compacting until the pore spaces get very small. And as they get very small, the water gets squeezed out, but sometimes what's left behind are some of the chemical sediments in the water, and these form the, you might think of the adhesive, the cementing agents that hold it together. I can't even read. This is cementation. I can't even read what that says. Oh, it says cement. Okay. Which are the things that hold it together. Now remember, this is over long periods of time, so it can form and get squeezed together pretty well. Okay? That chemical deposit, cement they call it here, is the cementing agent that holds those particles together, forming a new rock. It was some other rock, other rocks, many other rocks, but the pieces get combined together to form a new rock. All right? That was it for sedimentary rocks. Okay? Now, there are other great pictures in the book that are not showing in the slide set. Figure 1717 shows some limestone, looks like a road cut, and basically, folks, drive along the interstates, just about any interstate in Alabama, especially the northern ones. Down south, everything's flat. But where they have cuts, road cuts through, look at the rocks on the side. The odds are most of those rocks are going to be limestone. We just are in a place where the natural bedrock is limestone, which gives us really good soils, generally speaking, which makes our agricultural opportunity pretty good, okay? And that's a picture of some limestone. Take a look at this, then look at the road cuts when you're driving past. Not if you're driving, preferably if you're the passenger. Don't pay too close attention to the road cuts if you're driving. All right. Oh, and they do have a blurb here. I knew it was coming up sometime on asbestos. It's really worth a read. You'll be surprised how little of the asbestos is really harmful. But that is very harmful. And people don't distinguish, okay? If it says asbestos, people stay away from it like the plague, okay? Let me see if I can find it. There are about 6 commercial varieties of asbestos. 5 of these varieties are made from an amphibole material and are commercially called brown and blue asbestos. The other variety is chrysotile, and that's a serpentine family of minerals. It's commercially called white asbestos. White asbestos is the asbestos mined and most commonly used in North America. It's only the amphibole asbestos, brown and blue, that has been linked to cancer, even though most of it is the white serpentine that is not linked to cancer. And yet, if you see asbestos, people are staying away from it, lawsuits, everything else. Danger asbestos. Cancer and lung disease hazard. And it is, if it's the wrong kind. The odds are it's probably not the wrong kind, but you don't know that without testing. Sorry. Okay. Then there's another blurb. On the top of page 450, called Science and Society. It's using mineral resources. There was an earlier one on the cost of mining mineral resources. This one's on using mineral resources, and this is really a pretty good thing that has a few questions to think about. If you can find something in here that you would think would be a pretty good thing to do as a paper topic, you might want to consider that. I believe this is the one that talks about phosphate minerals, and I've already hit on that pretty hard. This is what brought it to mind. I knew about it from the my previous studies and stuff, but boy, this really brought the hazard to mind here. So anyway, there's that. Okay. Now we move into our third type of rock, and this is metamorphic rock. Metamorphic rock is rock that was previously existing. It was rock, already rock. It wasn't pieces of rock, it was rock. However, this pre-existing rock has been changed. That altering that we were talking about earlier on the slide set, this is where it shows up in now. Changed by heat, by pressure, sometimes by hot solutions, and it changes into a totally different rock. Okay? It metamorphosizes like the caterpillar to a butterfly. It changes completely into a, excuse me. Don't wake up. Okay. All right. Completely different rock. Mostly heat, pressure, sometimes hot solutions. The causes are usually associated with geological events. The pressures have to be really, really great. Okay? So sometimes this is shifting plates and things like this. It could be, volcanic eruption or something that really creates a lot of heat, a lot of pressure, combinations of stuff. Okay? Could be the movement of the crust. That's the geologic. That's the tectonic movement. That kind of stuff. Heating or hot solutions from magma intrusion. That's what I said. Volcanic activity. Even though it doesn't reach the surface, it could be coming up and changing things somewhere down deep. Okay. Temperatures must be high enough to cause recrystallization, but not melting. So it's a really fine line there. If you get too hot, it melts. Once it melts, what kind of rock does it become? What rock is from molten material?
Igneous.
Igneous rock. But if it's just hot enough to recrystallize but not melt, then it becomes metamorphic rock. So that's always the dance that's going on here. Now here are a few examples of this. We're going to start with, remember shale? Shale was what kind of rock? Forms in layers. Sedimentary rock. What kind of sedimentary rock? There's two kinds. Huh?
Plastic.
Plastic, yes. And what does shale make from? Boulders, gravel, sand. The shale was from silt or clay. Probably clay. Very fine particle size. Settled out in sheets. Okay? That's shale. That's shale. Sedimentary rock. But then these sheets get buried, 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 deeper, 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 and then something happens, heat, pressure, some combination of things happen, the shale turns to slate. Now where do we find slate? We have a piece of it in our bathroom downstairs, and it came from New Orleans. My wife picked it up there because way back, I don't remember when it was, there was a major fire that went through New Orleans. All the roofs caught on fire because most of the roofs were made out of, I think, cedar, whatever they call strips of cedar. Cedar splits into strips really nicely. It repels water because of all the oils in it and stuff, but it burns like crazy because of all the oils in it and stuff. Cedar shakes, is that what they call them? Something, yeah, okay, cedar shakes. So they decided to pass an ordinance saying you can't use cedar anymore for roofs because it was made to the fire. This is way, way back. And so New Orleans was a pretty rich city back then. This was before Katrina, of course. And so they started importing shale, I think from Pennsylvania or somewhere. And they made, not shale, slate roofs. Ever hear of that? Okay. Our church is the older church in south side of Birmingham. It has, the older part of the church still has slate roofs. Okay? That is shale, which was a sedimentary rock that underwent metamorphosis and it became much harder, but still in sheets, very flat sheets. That's why they made roof materials out of them, because it was easy to split in the sheets. That made slate. But if it undergoes even more heat, more pressure, then it can change again to schist. Okay, be sure you get the letters in the right order there. Okay, and the schist is another metamorphic that came from the slate. And then, from that, if it undergoes even more heat and more pressure, it becomes nice. Nice rock. No, okay. Nice. Remember that picture of that rock that had all the curving? That was nice. That has really undergone a lot of pressure, differential pressures. It's lost that flat sheets that you had up here in slate and shale and slate. Now it's all gnarled, okay? And those crystals have undergone incredible changes, and that's nice. If you undergo more heat and more pressure, guess what? It melts. And then it becomes molten rock becomes igneous rock. So it becomes granite again, okay? Which is an igneous rock, okay? Not a metamorphic rock. That's because it melted. Okay, that was a sedimentary, classic sedimentary rock, mostly from probably claystone, shale. Okay, then let's go to what kind of limestone? It's sedimentary. What kind of sedimentary?
Plastic.
Nope. Chemical. Okay, chemical sedimentary. It came out of solution somehow, you know. And so limestone under enormous amounts of pressure, high temperatures and stuff, its chemical structure changes. The crystal structure changes. And it becomes one of my favorites, marble. When my wife said, we wanted to redo the kitchen, and she said, I don't know what to use for the countertops. I thought that everybody does granite. So she said, I think I'll go with marble. Yes, okay, I love marble. Okay. But it's used to be limestone. Limestone is pretty easy to grade away, dissolve away, pit and stuff like this. Marble, hard stuff. It's going through a metamorphic change. And it's a new crystal structure, very, very hard. Now it is fairly brittle, and it will etch a little bit with acid and stuff like this, so you try to keep vinegar off of it and that kind of stuff. But that's a metamorphic rock. But what happens when that gets even more heat and more pressure? It actually melts, and you go back to calcite, which is a igneous. Okay, so it goes around, comes around. Okay, here's another. What is that? Sandstone. What kind of rock is that?
Sedimentary.
Sedimentary. What kind of sedimentary? That should be easy. Sandstone?
Plastic.
Plastic, of course. Okay. Plastic sedimentary rock. From sand that deposited particles. Okay. And when it gets heat and pressure, it goes into a type, and it sounds like quartz, but it's not. It's quartzite. Quartzite. Okay. And I think some of countertops are really made out of this as well. Some of it may be manufactured, which would be actual minerals then, but the quartzite is a very hard surface because sandstone is mostly quartz, right? So when it gets compressed together and the crystalline structure gets altered, then it becomes quartzite, which is a metamorphic rock. Okay? But then if more heat and temperature is added, what happens to it? It melts. When it solidifies again, it's what? It's an igneous rock again because it came from molten material. You're absolutely right. Okay? So when we say all rock was one time igneous rock, it may be all rock was one time or 7 times igneous rock, as we kept going through this process. But you can even have igneous rock. And this happened to be fine-grained igneous rock. Coarse-grained, maybe not as well. It can undergo a great amount of heat and pressure and stuff like this, change its crystal structure. Whereas this was clay sedimentary rock over here, this is very fine-grained igneous rock. It can then also become a schist. And you may not be able to tell whether that schist was originally igneous or originally sedimentary. Who cares? It's now changed because of the heat and pressure, and it's become schist, and you add more and it becomes nice rock, okay? And add even more heat and temperature, heat and pressure, it melts and becomes granite, which is igneous rock again. Okay? Now this is really leading to what the last topic is about. I'm not sure we're quite there yet, but before we do, there's a guy, people behind the science that's mentioned here, and his name is Victor Moritz Goldschmidt, okay? Late 1800s, early 1900s, okay? He was a Swiss-born, but Norwegian chemist, okay? And I have a feeling, I can't remember for sure, if he then didn't wind up in other places as well. Göttingen, I'm pretty sure, is German, so he moved around a bit. But anyway, he was one of the earliest workers in what we call geochemistry, actually looking at chemical composition and how it relates to geology. So, pretty impressive character himself. All right, now there is at least one more thing in metamorphic rock before we get to what I thought we were going to, and that's this. Another way to classify metamorphic rock. One way is by foliation. Okay. When you see that prefix, foliation, what do you think of? Again? Leaves, foliage, exactly. Leaves. What do we call sometimes the pages of the book? Leaves. In fact, was it Whitman maybe? That the whole book of his was Leaves of Gold. Maybe I got the wrong author, but yeah, that's what we're talking about. Sheets of things, foliation sheets. In any of your courses, do you put together a portfolio? Maybe not. I've had some commercial art majors before. They put together portfolios. Those are things in sheets, demonstrating their work. Okay? Foliation. The alignment of flat crystal flakes into sheets. Okay? So, metamorphic rocks, if in the process of modifying the crystal structure, some of these are flat crystals, if they get compressed into sheets, they, what we call foliate. Caused by the pressure on the parent rocks, the rock cleaves along these planes between the aligned grains and makes for very specific foliation there. Okay? Now, so you have various degrees of foliation. That's one way we classify. Or, if they don't, they're called non-foliated. The parent rocks consist mainly of one mineral. The grains are not aligned in the sheets, and remember that nice rock that we saw? Its sheets had been deformed, but it still was foliated. Probably not a very coarse foliation. And that's how we classify this. Okay? Those that I got this backwards here, I don't know why. If the parent rocks did not have this characteristic flat crystals, they were three-dimensional crystals, they were usually non-foliated. Quartzite and marble, non-foliated. You don't break those into sheets. Okay? Quartzite, remember, coming from sandstone that has been metamorphosized. Very finely foliated would be your slate. Remember, that's right up there underneath this shale, okay? The first stage. The finely foliated was schist, because the slate, remember, that comes out in the very, very finely foliated slices that you can use for roofing. Not quite as finely foliated was the schist, and then the coarsely foliated, that one we saw, very coarsely foliated, nice rock. Okay. That's your nice. The G is silent, by the way. Okay? Any questions on those? One way to classify metamorphic rock by the foliation. Either it's not foliated, very finely foliated, or very coarsely foliated. Okay. Here's same figure we saw before, only in smaller. Okay. Don't know why they repeated it here. But here is a piece of marble. Okay. I don't recall seeing a similar piece of sandstone. Yeah, we did. Remember the one with the little shell at the bottom? Okay. You didn't see the obvious crystals in it because the limestone, the crystals are usually very, very small because they came out of solution. Here they have been pressured into larger crystal size, and boy, I just love the appearance of marble. Okay? It's a coarse grain metamorphic rock. Okay? Usually your limestone is a little bit finer grain, so the pressure and the heat has made coarser grain. Okay? Here is that same banded metamorphic rock. This is a nice rock. Okay? This is, pretty sure it says that somewhere here. I think right there it says, no, that's years. This banded metamorphic rock, very old. Well, it doesn't seem to list it there, but I know somewhere they think it's about 3.8 billion years old. That's pretty close to the age of the Earth, okay? And I'm pretty sure somewhere here it specifies that is nice, okay? Okay. Now, and you can tell it's undergone a whole lot of pressure. For those, if you think about every one of those bands was one time horizontal, okay? In order to get twisted and bent and done like that, that had a whole lot of pressure. And probably a fair amount of heat too. Okay. And the final topic here, 17.5, is the rock cycle. Okay. If you haven't already noticed, rocks are transformed into new types by the Earth's interior and exterior dynamical processes. In other words, the surface of the Earth, the interior of the Earth, everything about the Earth is constantly changing. Slowly, okay, I'm not saying it's happening fast, unless you have a volcanic eruption or earthquake or something, that's pretty rapid, but most of the time it's pretty slow, but it's always happening. There's more pressure on top of what was there, it's changing that. There's something else happening somewhere else. You have the moving continents, very slowly, but they're moving. Seas advancing and retreating. Weathered and eroded material. Right now, every time it rains, a little bit of something gets worn off from something else. If it's a really serious storm and the water's rushing really fast and carrying with it other particles, carrying up other things underneath it. We'll talk about that in a later chapter. Okay? The weather and erosion constantly happening. Slowly, but happening. So everything is changing. And this next one is one of my favorite illustrations. It's bizarre, but it's pretty good. Okay? You can start anywhere you want to on it because it's a cycle. It goes in cycles. So let's start with igneous rock because all rock was at one time igneous rock. What happens to that? Well, it's exposed to the weather, it gets eroded, broken off, chipped off, and then ultimately forms sedimentary rocks, so little pieces do. The sedimentary rocks, or the sediments, bottom out, get what is the two process of lithification? Let's start with C. Compaction and cementation. Very good. Okay? So as the sediments get compacted, they get cemented, that's the lithification process. And that becomes sedimentary rock. Okay? Now, also this igneous rock could get lots of heat, pressure, and stuff over long periods of time. It could actually metamorphosize into metamorphic rock. If it was igneous rock, it went straight to metamorphic. Okay? Or it went to sedimentary if it got broken down before that process happened. So let's go to the sedimentary rock. The sediments lithify to become sedimentary rock. Guess what can happen to sedimentary rock? It can get eroded and weathered and go back to being sediments again after only been a short or a long time as a sedimentary rock. It goes back to sediments and then gets into a sedimentary rock again. Or that sedimentary rock could metamorphosize, as we saw limestone becoming marble, as we saw shale becoming slate, becoming schist, becoming gneiss, okay? Lots of things can happen to that. The metamorphic rock can get weathered and eroded, just like any other, and become sediments again. Lithification, make it sedimentary rock again, round and round we go. The other thing that can happen to metamorphic rock, it can get more pressure and temperature and become different metamorphic rock, or at some point, so much heat it melts. If it melts, it goes back to being magma, and when it quits being magma, it becomes igneous rock again. Wow. Lots of ways to go, lots of ways to get there, and it's always happening. Very, very slowly most of the time. Some catastrophic issues could happen quickly. Most of the time, very, very slowly. Whoa! What was that? Sounded like something. Ah, there it is. A marker. Okay. That's the last slide. As I say at the end of every chapter, nothing replaces reading the chapter. Please, if you haven't read it now, go back and read it. Hopefully what I've said will make more sense when you read it. On the other hand, if you read it first, then whatever I say hopefully will maybe make it make more sense. But every time you hear it or read it, go over it again. Hopefully you'll get something different out of it. Once you've read it, the summary is not bad. I find it a little short here for such a packed chapter as we had, but it's pretty good. It has lots of italicized words. Those are pretty key terms. And then they list most of those key terms, so that list is pretty short too. They list them alphabetically, but they give the page number in which they were first introduced or defined or described. Then you have applying the concepts, which I find is the best thing to study for the test. Okay? Multiple choice questions, 43 of them. Again, a little bit shorter than most have been. The answers are given, but don't look at the answers first. You try to come up with your best answer, then look at the answer, see if you got it right. If you didn't get it right, see if you can figure out why you missed it. Okay? That's a great way to learn. If you can't figure out why you missed it, bring it to class, ask about it, we'll talk about it. We may find out it's an error in the book, or we may find what little word changed the meaning just enough to make it a different answer from what you expected. Questions for thought about a normal list here, maybe a little on the long side. For further analysis, only 4 questions. That's about normal, maybe a little short. There is an invitation to inquiry, building rocks. I don't see anything that great in that, but you may find something that you would find interesting there. And then the parallel exercises are a lot like the examples I gave in the text. Most of the time we've been avoiding them because they're based on the physics and chemistry found in earlier chapters, which you haven't had. A few of them you could do, so I'll let you look through that. Now, where are we now? Just after 4 o'clock, right? Which means we passed 3:45 and you didn't tell me to call roll again. Did you, huh? All right, so let's get roll call. Luis is still here. Lexi hasn't made it in today. Okay. Zarik is still here. Brianna is still here. All right. CJ's still here. Ethan's still here. Amanda's still here. Jordan's still over there. Yep. Okay. Jonah's still here. Patrick's still here. Maurice is still here. Cameron's still here. Derek's still here. Tegan's still here. Chris. Ah, there you are. Okay. Latricia, though, has not made it in today. Okay. Kevin's still here. Ian's still here. Edward's still here. Maya's still here. Michael Pruitt is trying to do it remotely. Ken's still here. Whoops. Yeah. Diamond's still here. Tamaya didn't make it in today. Ruben's still here. And Ryan's still here. Excellent. Way to go, folks. Okay. just sort of debating here just to hit discard key. All right. Let's at least get started on chapter 18. Now,
Are we supposed to be taking tests today?
yes, we are.
When is that going to happen?
What's that?
When is that going to happen?
That's what I was debating on. I think 4 o'clock's a little on the early side.
No, it's not.
Oh, yes, it is. Okay. But I would say let's get going on chapter 18. And when we come to a good break point, and I'll determine what's good enough as a break point, we'll probably stop there and give the test early. If that's okay with y'all. You think you can handle it? All right, good. All right, so let's get going on the slide. I hate to cheat you out of a penny of your tuition dollars, okay? But I will. No. All right, chapter 18 is something we sort of hinted at in the last chapter when we talked about moving continents a couple of times and shifts and things like this. This is the study of those moving plates, plate tectonics. Okay? The core concept, which you'll find on page 458, is Earth has an internal structure, and guess what? Cycles. You're going to see this word in so many chapters, or at least the concept in so many chapters. It's just amazing. Cycles materials between the surface and the interior. Okay? We're going to be talking about some of these processes now. But if you think back on even the astronomy chapters, what did we find there? You started with masses of gases. They formed into protostars, became stars. After a while, they blew up and sent gases back into the thing. And then guess what? The masses of gases reformed into stars. Cycling of the materials over and over and over. So that's the same thing happening here. Earth has this internal structure. It cycles materials between the surface and the interior, constantly mixing them, changing them, metamorphosizing them, and coming up. Now, this is a picture we'll see later. I don't want to spend too much time on it now because we don't have the background for it. But this just shows some of the major plates of our tectonic plates. Big old Eurasian plate, which is mostly Europe and Asia. That's where it gets its name. Okay? There's the African plate, not all of Africa, but much of it. There's the Arabian plate, most of Saudi Arabia there, but a few other pieces on it. There's the India-Australian plate. I don't know if you've ever thought of that. See, India is part of Asia, but yet it's part of a different plate, the same plate that contains Australia. There's the Philippine plate over here, which of course the Philippine Islands are part of. There's the Pacific plate, which is mostly underwater, of course, okay, here. There's the Antarctic plate down here. Now that makes it look really huge because you've taken a globe and spread it out into things, so it's not nearly that big. But here's the Pacific plate. And then there's the North American plate here, which includes not just North America, but about half of the North Atlantic Ocean. Okay? You have a very tiny little plate here called the Juan de Fuca plate here. The San Juan Islands off the coast of Washington State are in that plate, or part of that plate. Caribbean plate down here. The Nazca plate here, which is part of the South Pacific, nearest South America. And then you have the South American plate, which contains about half of the southern Atlantic Ocean, as well as all of South America. And then you bump into the African plate again and the Eurasian plate again. Okay. Don't sweat this. Now, here's something I haven't figured out. They have a green colored thing down here they don't have a name for. I have no idea what it is. I haven't found anything that ever told me why they did that, and if that's a separate plate or not. They put Juan de Fuca, which is just a little sliver you can't see, but they didn't name that if it does have a different name. It can't be part of the African plate, I don't think. It's not even connected to it. So Don't know what that is. But we'll get to this later. Let's start with a history of the Earth's interior. Now, we feel like the Earth was formed about 4.6 billion years ago when we were still part of that solar nebula. Don't know if the sun had yet become a star. Maybe had, because they think that was about 5 billion years ago, but this 4.6 is awfully close to 5 billion, so somewhere around the same time. The early Earth had a molten surface, melted surface, mostly from bombarding materials from that really active solar nebula you had there. I mean, there were just lots of things happening. The sun was blowing up, sending things out, they were flying back in. It was a mess. That may be when the Earth got split into Earth and Moon. We don't know, okay? But the early Earth was a molten surface, mostly from the bombarding materials. Now, I think also probably from the radiation, all those nuclear reactions happening on in the sun that were blowing up and sending things out too. Well, the surface cooled and crystallized, cooled very slowly, forming what size crystals? No. Slow cooling, big crystals. Rapid cooling, small crystals. Okay? So, form some fairly large crystals. And maybe that's where some of those great big old quartz crystals that we saw came from. Maybe they're that old. Now, the heat accumulated from that radioactive decay I mentioned earlier led to a second melting, this time of the interior. Okay? And much of our interior is still molten. Okay? Keep that in mind. The melting occurred in pockets, not throughout the interior. Keep that in mind, because that comes into play in what we're going to talk about later. And then they throw in a term here, differentiation. You feel like you're in a calculus class, right? Okay, not quite. Something. This differentiation is the melting and gravitational settling of the heavier metals down to the lighter metals up, lighter materials up, elements. It gave Earth its present stratified structure. Now, it's not a clean stratification. It's all mixed up and irregular, but generally the stratified structure. The outer core of the Earth is still molten and is mostly iron. A fair amount of nickel and perhaps some magnesium. I haven't figured out why magnesium's down there, but it seems to be. But iron and nickel mostly, but mostly iron. Okay? Now, how about at the very center of the Earth? Down there, the pressure, remember we talked about 10 meters of water makes one more atmosphere of pressure. Down near the center of the Earth, the pressure is about 3.5 million atmospheres of pressure. That's a lot of pressure. Okay? Temperature down there, about 6,000 degrees Celsius. Really, really hot. Now, the surprising thing is, the very inner core, the outer core is still molten. The inner core is solid again. And we're going to talk about that a little bit later. What's going on here? You have two competing things, pressure and temperature. Pressure tends to push it together and make it solid. Temperature tends to make it melt, okay, and make it a liquid. Well, obviously at the inner core, this pressure wins, and it becomes solid. The outer core, molten, okay? It's still hot enough to be molten, but not enough pressure to force it into being solid. How do we know that? Who's been down there to find out? Nobody. Nobody could possibly go down there and find out. Journey to the center of the Earth? Fiction. I don't even want to say science fiction. Fiction, okay? It's made up. No one has been down there. Literally, we barely scratched the surface, okay? We haven't even gotten very far into the crust of the Earth, much less anything near down there. So how can we say this with any kind of confidence? We're going to get to that. Okay? Here is the evidence of the Earth's internal structure. Okay, that was history of the Earth's internal structure, of Earth's interior. This is evidence of Earth's internal structure. This is 3.2, basically. Okay? Here's the evidence. The Earth has a magnetic field. Now, how does that give us any evidence that our internal structure is like it is? Well, this came from the first half of the book. I'll give you a hint. The only way you get a magnetic field is to have a moving charge. Moving charges create magnetic fields. So, well, we know the Earth's spinning. We determined that, right? It's spinning. That was the first 3 chapters. Earth is spinning. Now, if we were all solid, if the Earth was totally solid, we would all be spinning together. There wouldn't be any reason to have any charges, okay? But because the Earth has an outer shell and then an inner molten core and then an inner solid core, then when the Earth spins, that liquid tends to just get brushed past the other cores. And when it gets brushed past, it knocks off charges, especially since that's iron. Remember, mostly iron. Iron has charges. Iron is also magnetic. And that's where the moving charges come from. That's what creates the magnetic field. So there must be some friction in there, internal structures that's different, solid, molten solid, that creates the charges. Where they get knocked off as that spinning occurs. That's one. Gravity effects. Oh, wait a minute. Everybody has gravity. Every object has gravity. Well, the gravity effects, we know about what the density of the crust is, right? We can dig in the crust. We can sample it. We can take density. We see what the gravitational pull of the Earth is. No way that's the same density as the inner part of the Earth. We know the size of the Earth. If we were all that density, we wouldn't have nearly as strong a gravitational field. So the gravitational field indicates you've got denser and denser and denser materials somewhere down there. So the gravitational effects also tell us there's denser materials inside. Okay? Heat flow. We can study the flow of heat. We know what happens with friction. We know what happens with all that pressure. It's got to be producing lots of heat. We see heat come out from geysers, from volcanoes, from other activities like this. We know there's heat. We study the heat flow, and we have a good idea what the constitution of the Earth is, what the characteristics are, how rapidly heat travels through that material. So that gives us a clue. Okay? Now, this gives us the biggest clue. Vibrations in the Earth. Why does the Earth vibrate? Earthquake. That's exactly what earthquake is vibration of the Earth. Okay? Shaking. Earthquake or shakes. Okay? So, when that happens, seismic waves are released. Now, seismic waves come in 2 forms. Well, 3 forms, actually. We'll get to that a little bit on the subsequent slide. The seismic waves radiate out from wherever the earthquake was. They travel through the Earth. Okay? Now, as they travel through different parts of the Earth, they either lose speed or pick up speed. And we can measure that. Okay? Also, sometimes they get blocked altogether. Why? The study of that helps us understand Earth's internal structure. Okay? They radiate outward from the earthquakes, also noted from nuclear explosions. A nuclear explosion is a big enough thing to happen that if that happens anywhere, we have seismologic gatherers, equipment scattered all over. 2 things that science has been able to accomplish that no other governmental entity has ever been able to do. It's gotten countries to cooperate in two areas: seismologic measurements and tidal measurements. Those countries that border oceans, they all have equipment out there measuring tidal waves that communicate with all the others all over the planet. The other is seismologic. Fantastic system. So when there is an earthquake somewhere, everybody gets the readings from it and start analyzing. And if there's something that doesn't quite seem to be an earthquake, but is pretty powerful, and it doesn't have all the characteristics, then we know someone let off a nuclear weapon. So you can run, but you can't hide. Okay? So when some folks have claimed they set off a hydrogen bomb, if there was some seismologic activity detected, it didn't happen. Okay? Not a hydrogen bomb. That's way too big. So that's political. We won't go there. All right. That was just thrown in at the bottom. Okay. So let's look at as I said, three types of waves, seismic waves that come from earthquakes. Now they have multiple names, so get the names straight in your head. And I'll try to give you some hints to make it happen. There's the P wave, okay? Really creative name. That P can stand for one of two things. It probably only stands for one, but think of it in terms of the second one as well. P meaning primary, the first wave, the wave that goes out first, the first wave, primary, first wave, P waves. But also think of this, it's a longitudinal wave, which may not make any sense to you, but that means it's a compression wave, so think of a pressure wave. Compression, pressure, longitudinal wave. Now, what does a longitudinal wave mean? That means, okay, a wave has two characteristics. A wave itself is moving, okay? The energy of the wave is moving. The actual material is moving, and the energy of the wave is moving. A longitudinal wave, or a compression wave, the material moves in the same direction as the energy. In fact, you're hearing whether you want to or not, a compression wave right now. If you hold your hand in front of your mouth when you're talking, you'll feel little spurts of air hitting your hand, right? Because sound is a pressure wave, okay? What it means is the air molecules are pushed together and separated, compressed and birefracted or something like that. So you have that constantly going on. That's a pressure wave. The air molecules are doing this, moving in the same direction as the energy from the wave is, going out. Okay? Your eardrum is sensitive enough to pick up those tiny little waves that made it to your ear, that little pressure wave, and that's what makes you hear. It goes through all sorts of amplification in there. Your brain interprets it, and you can understand what's being said. Amazing, if you really think about it. Absolutely amazing. So that's what it is, a compression wave. Pressure is going in the same direction. These are the fastest waves, which makes them the primary waves. They get there first, first. Okay? The fastest waves. Now, here's the key. Pressure waves move through solid material. In fact, they move through solid material way better than they go through there's a word that's used both for liquids and gases. I can't think of it now. Goodness gracious. Fluids. A liquid and a gas, both considered fluids. Okay? I don't know if you ever call it gases or fluids, but it is. So a P wave, a pressure wave, will go through solid materials and it goes through fluid materials. Now inside the Earth there's not that much gases, so they're all liquids there. But they'll go through solids and fluids, or liquid materials. That's the key. The S wave, guess what that stands for? Secondary wave, exactly, and that's really what it stood for. But here's another thing you can have it stand for. It's a shear wave. Shear is another name for transverse. Longitudinal is in the same direction. Transverse, trans means not in the same direction. How I think of a transverse wave, and this goes back to when I was a kid. I was a weird kid, I guess. But whenever we had the hose stretched out there in the yard, watering something or something, one of the things that I don't know why I just love to do is get the hose and do this. Go up and down with it, and then watch that travel, snake down to the hose. It petered out pretty quickly, but I love seeing it do that. I don't know why, I just did. Well, think of that. The motion of the hose, my motion is up and down, but the energy of the wave is that way, down the hose. Transverse, shear, okay, different directions. Longitudinal or compressional, same direction, okay? That's the key here. It's the second fastest. Secondary wave, S wave, second fastest wave. Here's the key here. Because the motion's up and down and the transmission's that way, that will go through a solid. But can you imagine going through a liquid that way? You go up and down and it just dissipates. So it will not travel through liquid materials. P waves will, S waves will not. Primary waves will, compression waves will, shear waves or transverse waves will not. And then finally we have the up and down waves. This is like waterways and things like this. These are surface waves. When that energy, these seismic waves which come somewhere in the earth and make their way out, when they reach the surface, they can't keep going out because there's nothing else to do. Air doesn't transmit them all that well, so they make a surface wave, and that's the last time. The up and down, crest and trough wave, a lot like water waves. And if you've ever seen a picture or an illustration that they took, motion picture, of when they did blow up a nuclear weapon, and you see the waves going out, dust or other things like that, those are your up and down surface waves. It literally, the energy goes out like that. Okay? These are the slowest of the waves. Now, they occur where either the S waves or the P waves reach the surface and then they start moving out. Not in the same direction from here to there, but they start moving sort of laterally. Now, sometimes these are recorded as the biggest waves, okay? But they're not, they're the slowest. I think they say, yeah, slowest of the three. All right. Now, here's the example. I gave speech, sound, they give a spring, okay? Not a spring you do this to, but a spring you do that to. If you've ever done something like this, now I've never gotten a spring to stay that level. I don't know how they did it. But if you did, and you pressed in and pulled back, you'll see that compression and rarefaction move down. See, here's the compression. There's the compression to begin with. There's the rarefaction. Then the compression, they didn't draw it well here, goes here, the rarefaction there, compression here, rarefaction there. They didn't draw this one very well. But that moves down in the same direction of the motion. That's the key. That's what makes it a primary wave, a P wave, a pressure wave. Okay? Particle motion in the same direction of the wave propagation, or the energy of the wave. Whereas, here's my hose, that's their cord, the up and down motion, and you'll see that make its way down here, and actually sometimes bounce off and come back at you. Okay? That's a transverse wave. The motion's up and down, the wave propagation is perpendicular. Secondary wave, slower wave, but not the slowest. So that's the represent two types of seismic waves. Okay. Now, how does all that contribute anything to the Earth's internal structure? Okay. What we're going to do now is tell you what we think is happening Later we'll tell you why we think it's happening. Tying that in. So we gave you the background. Now we're going to tell you what we think, and then we're going to tell you how that tells you what we think. Something like that. Three main zones of the Earth's internal structure. First is the crust. The crust is an incredibly thin little shell. Okay? When I say thin little shell, it doesn't go down more than a few miles. Now that sounds thick to me, but compared to the Earth, that's a thin little crust. Okay? Outer thin shell. Most of all of our mining and drilling and everything else has always been in the crust. Occasionally, some really deep, deep stuff that's going on. I think the Russians or the Soviets have done some. They've actually gotten into the next layer. But most of everything we've ever done has stayed in the crust. Okay? The next thing we hit is the mantle. Okay? Much, much thicker than the crust. I mean, enormously thicker. And then you have the core at the central part. Now, the core is actually made up of two parts, but we'll get there later. So here's what we've got. This little brown around here is an illustration of the crust. Very, very thin. Okay? The mantle is a little bit lighter brown to the tan here. This is all the mantle. Later we'll find out why there's two colors for the mantle. Okay, but this is the mantle. The mantle is by far the biggest chunk of the Earth. Okay, the mantle. Then you get into the core, and that's here, it's really hot. Okay, and that core is the outer part is molten, the inner part is solid again. Okay, we haven't gotten to that yet, but we will. Okay, now a couple of things about this drawing. This is just an illustration. It doesn't show detail at all. Okay? I'm guessing the relative dimensions are not far off, but this is not a clean, smooth boundary between the crust and the mantle at all. It's probably really jagged and irregular and everything else. And then this one that we'll talk about later is definitely not that smooth and rounded. Okay? Okay. This one, at least down here, it looks fairly diffuse. Up here, it looks like it's more distinct. It's not. It's really jagged and uneven, irregular. Okay? And probably in here is probably the same deal, too. I don't know. I've never been there. Okay? So I don't know for sure. But I bet you it's not nearly this clean and neat and pretty. Okay? So let's talk about the crust. This is on page 461. Okay. I definitely don't want to get past 5 o'clock. Okay. So don't let me get past 5. Okay. I don't want to go to 5:15. I want to stop well before that. The crust covers the entire Earth, everywhere. Now, I can almost imagine some of you saying, "What about the ocean?" The ocean is a little puddle in the crust. Okay? Underneath the ocean is part of the crust. We'll get to that a little bit later too. Oh, right here is where we get to it. There's the oceanic crust. The ocean all sits above the oceanic crust. The oceanic crust, though, is much thinner than the continental crust. The oceanic crust is mostly basaltic rock. Do you remember what basalts were? There will be some characteristics of basalt. A hint came from largely volcanic activity. Is what? Okay. Formed by lava. So lava formed above the surface. So what would be true about it? Say again?
Igneous rock?
Can't hear you.
It's an igneous rock?
It's an igneous rock. You're absolutely right. Basalt is an igneous rock. Very good. Okay. What else? Well, it came from molten material. Very good. Okay. Now, what else? Especially since it's formed underwater. What's the cooling rate? Very rapid. So what did that tell you about the crystal size? Very small, which made fine grain. And since it came from magma, which then became lava, that came from deep in the earth, what's deep in the earth? What's the most predominant element down there? Iron. Okay, if it's iron, what are characteristics that come from iron, heavy iron rocks? It's part of the way there.
It's heavy.
Huh?
It's heavy.
It's heavy, it's dense is part of it, and it's also dark. It's light in weight, but light in color. Okay? Not light in weight, not light in color, dark and dense. Okay? The granite rock is light in weight, light in color. Okay? So it's denser, right there it was. The basaltic rock is denser, fine grained, small particle size, dark rock, largely iron, but with much thinner crust. The continental crust, granite rock. Tell me something about granite rock. Characteristics of it. Oh, and by the way, did I say, I don't guess I actually verbalized it. Since we did finish chapter 17, it was 17, wasn't it? Yeah. Today, that means the last 30 minutes on Tuesday will be the test of 17. Okay? And the odds are the 2 hours before that will be the lab on 17. No. Yeah, the lab on 17. Definitely. 2 hours before. The last 30 minutes will be the test, and we will go till 5:45 on Tuesday. Yay! Okay, yeah. Expected to hear all sorts of cheers there, but I didn't hear it. Okay. So, the last 30 minutes will be the test on 17. The 2 hours before that will be the lab on 17. That will be a computer lab. We'll go to a computer lab somewhere on campus here. I'll find one beforehand, hopefully, and we'll go there and do our lab. I'll also take out the rock samples and show you that. Okay, so just wanted to remind you of that. Okay. Also, I said it before, but talked about the test, how to study for it. Okay, so that's the continental crust. Let me go on and show you the illustration of that. Here's the ocean. Here's the oceanic crust, dark, fine grained, basaltic rock. Okay? Over here, though, is the continental crust, much thicker. This is thin, this is thick, but this is light density, light in color, granite rock, but typically, now this is bizarre, large crystal size, coarse rock, coarse grain rock, because granite is a coarse grain. It cooled slowly, probably when the earth was cooling slowly from the surface being molten. Remember where we talked about that? And that made the continental crust. Somewhere under there is the mantle. Now this is much more realistic about how uneven those boundaries are. They're not smooth and slick and everything else. They're very uneven. Okay. Now, getting to that, the boundary between either the oceanic crust or the continental crust and the mantle, that's called the, goodness gracious, Mohorovicic discontinuity, or something like that. Quite often we just call it the Moho, okay? It's a lot easier to say. Mohorovicic, named after somebody, so if you want to write a paper on him, that would be fine too. Discontinuity is the boundary between the crust, either oceanic crust or continental crust, and the mantle, which is somewhere way, way deep in there. Okay. Now, the seismic wave velocity, I find that this is sort of backward in how they say this. The seismic wave velocity increases sharply when it goes from the crust to the mantle. Well, guess what? Most of the seismic waves originate in the mantle and go to the crust. So I would have said it the other way. The seismic wave velocity decreases sharply when it goes from the mantle to the crust. But it's true both ways. Even if you had earthquake up here, it would change speed when it gets there. Now, why would that be? The mantle is much denser. It's more packed, so the velocity, wave velocity travels much faster. Is faster. Okay. I was thinking we might get to, in the text, theory of plate tectonics, but I'm afraid we might not get there. So why don't we stop at the mantle here? Okay, I'm sorry. I know y'all are disappointed, but get over it, okay? We'll pick up and go with the mantle next, okay? So, this would be a decent break time. I know you just had a break not long ago, but if you want to get up, stretch, get your formula and equation sheet together. That would be a good thing to do. Let me get this shut down. I'm going to